Right now, as you read this, a construction contract worth billions of dollars sits signed on a desk at NASA headquarters. Not a contract to visit the moon, not a contract to plant a flag, collect some rocks, and return home within a week. A contract to build something permanent. A place where human beings will live, work, and remain on the lunar surface continuously for months, then years, on a world that has never once in 4 billion years offered anything resembling hospitality to anything resembling life. The date was the 26th of May, 2026. NASA awarded the first formal construction contracts for a permanent moon base. The recipients were Blue Origin, Astrolab, Lunar Outpost, and Firefly Aerospace. The dollar figures were significant, the ambitions were larger still, and almost no one in the coverage that followed paused long enough to ask the question that actually matters. Not whether we can reach the moon, we can. Not whether we can land structures on its surface, we can do that too. The question that matters is what happens after the structures land. What happens when you try to keep them functioning, not for a week, not for a visit measured in days, but continuously, across seasons that last months, across years of exposure to an environment that does not merely ignore human presence, but actively dismantles everything we bring to it. That question changes the entire conversation, and the answer is far more difficult than any press conference will tell you. If you find yourself drawn to deep examinations of the hardest problems humanity has ever attempted, do me a small favor and hit that like button and subscribe. It genuinely helps this channel continue making content like this. Now, find somewhere comfortable. What follows is going to take time. Let's begin. To understand where this story begins, you need to understand the specific moment that set it in motion. On the 24th of March 2026, NASA convened a press event it named Ignition. The name was chosen deliberately. The agency announced a fundamental restructuring of its Artemis program around a single objective that had been discussed, proposed, funded in pieces, and abandoned in pieces for decades. This time, the language left no room for ambiguity. The United States would construct a permanent installation on the surface of the moon, not a temporary outpost, not a sortie camp where astronauts shelter for a few days before climbing back into their lander. A phased, continuously expanding base positioned near the lunar South Pole, designed to support human beings living and working on another world for months, and eventually for years at a time. The committed funding was $20 billion, spread across 7 years. Construction would flow through commercial partners whose launch vehicles, landers, and surface systems would do the work that NASA's own hardware had once been expected to perform. The timeline was divided into 3 phases, beginning with robotic scouting missions and concluding with sustained human habitation infrastructure sometime in the early to middle part of the 2030s. NASA Administrator Jared Zachman framed the announcement in language designed to signal permanence. America would not relinquish the moon again. The political commitment, at least in that moment, sounded absolute. The momentum accelerated within weeks. By May 26th, the first contracts were signed. Blue Origin would provide the Mark 1 Endurance lander for what the agency was now calling Moonbase 1, with a target launch window no earlier than the fall of 2026. Astrolab and Lunar Outpost would develop the surface rovers. Firefly would build the orbital relay infrastructure that would keep the base in contact with Earth. What NASA unveiled was not the image of a single habitat module sitting alone in a crater. It was something far larger in ambition. A distributed network of assets extending across hundreds of square miles of South Pole terrain, pressurized habitats, science stations, power generation units, surface roads packed from regolith, communication relay towers positioned on elevated ridgelines, rover garages, construction staging areas, and a fleet of autonomous scouting drones called Moonfall, designed to survey terrain without human guidance. The scale was not modest by any measure. It was the most expansive surface infrastructure program NASA had articulated since the final years of Apollo, and for once, there appeared to be genuine institutional energy behind it. The backdrop helped. Just weeks before the contract announcements, Artemis II had concluded successfully. 4 astronauts had traveled around the moon and returned safely to Earth, validating the Orion spacecraft, the Space Launch System rocket, and the deep space life support architecture that every subsequent crewed mission would depend upon. Artemis 3 had been restructured as an orbital docking demonstration scheduled for 2027. Artemis 4, planned for 2028, would attempt the first crewed lunar landing since December 1972. After that, NASA intended to deliver crews to the surface every 6 months, incrementally building capability and infrastructure with each rotation until the base achieved the kind of self-sustaining operations that continuous occupation demands. The coverage was enthusiastic in the way space coverage almost always is when the images are beautiful enough. Animations showed habitats gleaming on crater rims, bathed in low golden sunlight, with suited figures moving purposefully across silver terrain. Infographics laid out the 3 construction phases with confident arrows and clean timelines. The narrative was clear and satisfying. Humanity was returning to the moon. This time, we were staying. Almost no one stopped to ask the harder question. The harder question is not whether we can land on the moon. Apollo proved that across 6 successful missions spanning 3 years. The harder question is not whether we can design a structure capable of sitting on the lunar surface. Engineering firms are already doing exactly that, with hardware in various stages of fabrication. The harder question is what happens to those structures once they have been delivered. What happens when the systems inside them must function not for a week but for a year? Not for a single crew rotation but across a decade of continuous occupation in an environment that attacks every material, every seal, every circuit, and every biological system through multiple simultaneous mechanisms, every hour of every day without a single pause. That question does not have a comforting answer, and grasping why requires first understanding what the moon actually is as a physical environment, not the moon of imagery and mythology, not the simplified moon described in textbooks for children, the real moon, the moon that 12 human beings walked on and came back from warning about. The lunar surface has no atmosphere. This fact is recited so routinely that it has been drained of its meaning. People hear it and understand only that there is no air to breathe. That is the least significant consequence of atmospheric absence. The absence runs far deeper, and its implications ripple through every engineering challenge a permanent base must solve. No atmosphere means no ambient pressure outside the habitat walls. Every pressurized structure on the moon is, in engineering terms, a sealed vessel holding breathable air against the void of space. If a wall in your home develops a hairline crack, you feel a draft. If the wall of a lunar habitat develops a hairline crack, the pressure differential between inside and outside drives decompression with a force that leaves no margin for error and no time for a measured response. Every seal around every window, every airlock, every cable penetration, every equipment hatch is a potential failure point. And every one of those failure points sits under constant mechanical stress for as long as the base remains occupied. No atmosphere also means no thermal buffer of any kind. On Earth, the atmosphere functions as an enormous medium for heat distribution. Air carries warmth from sunlit regions toward shaded ones. Wind layers mix temperature gradients across vast distances. Clouds intercept solar energy before it reaches the surface. Atmospheric humidity stores and releases thermal energy with enormous capacity. None of these mechanisms exist on the moon. Heat moves at the lunar surface through only 2 pathways: radiation outward towards space and conduction downward through the soil. There is no convection, there is no gas blanket softening the transitions between hot and cold. The result is a thermal regime of almost incomprehensible severity. At the lunar equator, surface temperatures swing from roughly 127 degrees Celsius under direct sunlight to negative 73 degrees during the 2-week lunar night. That is a range of 300 degrees occurring across a cycle of 29.5 Earth days. At the South Pole, where NASA intends to build, the conditions are different but no less punishing. The sun never climbs more than a few degrees above the horizon. Elevated terrain near formations like Shackleton Crater receives near-continuous sunlight for much of the lunar year, which is precisely why engineers selected the South Pole in the first place. Even the best illuminated sites, however, experience periodic shadow. Some candidate locations endure darkness lasting several consecutive Earth days. The permanently shadowed crater floors nearby, where ancient water ice has accumulated over billions of years, register temperatures below -200 degrees Celsius. Some measurements place them below -230. These are among the coldest naturally occurring temperatures anywhere in the inner solar system. No atmosphere means no protection from radiation. On Earth, the atmosphere above you provides shielding equivalent to roughly 10 meters of liquid water. The planet's magnetic field deflects most incoming charged particles before they even approach the upper atmosphere. The Moon has no meaningful magnetic field, and nothing resembling an atmosphere worth measuring. Every particle of galactic cosmic radiation that traverses the universe, every proton and heavy ion accelerated to near the speed of light by distant stellar explosions, arrives at the lunar surface carrying its full destructive energy. Solar particle events, sudden ejections of energetic protons during solar flares, and coronal mass ejections strike the surface without the slightest attenuation. The first direct surface radiation measurements came from China's Chang'e 4 lander, which recorded data from the lunar surface during 2019 and 2020. The readings placed the absorbed dose rate at roughly 2 to 3 times what astronauts experience aboard the International Space Station in low Earth orbit. A human being exposed on the unshielded lunar surface would accumulate approximately 400 millisieverts of radiation per year from galactic cosmic rays alone. NASA's career exposure limit for astronauts is 600 millisieverts total. A single large solar particle event could deliver a lethal dose in a matter of hours. No atmosphere means no protection from micrometeorites either. Particles of space debris that would burn harmlessly in Earth's upper atmosphere arrive at the lunar surface at velocities reaching 70 kilometers per second. Over time, this constant microscopic bombardment pits optical surfaces, erodes thermal coatings, degrades solar panel cells, and generates additional fine material that compounds the already severe dust problem. This is the environment into which NASA plans to install a permanent crewed facility, not for a visit measured in days, as Apollo managed with extraordinary care. A permanent installation that must survive thousands of thermal cycles, continuous radiation bombardment, relentless dust infiltration, micrometeorite erosion, and the perpetual mechanical strain of holding breathable air inside a sealed structure sitting on the surface of an airless world. The distinction between a brief visit and continuous habitation is not a matter of degree, it is a matter of kind. Apollo succeeded in part because it was so brief. Astronauts landed, completed their work, and departed within 3 days. Even within those 3 days, degradation was visible and measurable. Dust abraded the outer layers of spacesuits. It clogged wrist joints and stiffened glove mechanisms. It scratched helmet visors and reduced visibility during surface operations. It worked through every interface between suit components, despite every precaution the crews could take. Once astronauts returned to the cabin and repressurized, the particles they carried inside became airborne in the enclosed volume, settling in equipment and entering the respiratory systems of every crew member. Harrison Schmitt, the geologist who flew on Apollo 17 and remains the only formally trained scientist to have walked on the lunar surface, experienced an immediate reaction the moment regolith particles entered the cabin. His nasal passages swelled. His throat became irritated. His sinuses remained congested for hours. He referred to it as lunar hay fever. Every one of the 12 people who walked on the Moon reported some version of this response during stays that lasted between 22 and 75 hours. 75 hours. That is the number that should stop anyone who is thinking seriously about permanent habitation. Apollo's longest surface stay was 3 days. During that time, boot soles eroded measurably, suit fabric frayed at exposed edges, vacuum seals on sample containers were compromised. When the astronauts left, they left all of it behind. The suits, the landers, the degraded equipment, every piece of hardware that the Moon had damaged was simply abandoned as the disposable cost of a short mission. A permanent base cannot make that calculation. The suits must be reused across hundreds of excursions. The airlocks must cycle thousands of times. The habitat must hold out the dust across years of continuous operation. And this is the point where lunar regolith transforms from an operational inconvenience into a relentless and compounding adversary. Lunar dust is unlike any material that exists on Earth. Terrestrial dust particles have been shaped by billions of years of wind erosion, water transport, and chemical weathering. They are rounded and smooth. They settle in predictable ways. They can be swept, collected, or washed from surfaces without unusual difficulty. Lunar regolith has experienced none of these processes. The Moon has no wind, no liquid water, no chemical weathering cycle. Its surface material is produced entirely by impact events. For over 4 billion years, micrometeorites have struck the lunar surface at velocities of tens of kilometers per second, pulverizing rock into fragments spanning every size. The finest of these particles, those measuring less than 20 micrometers across, constitute what scientists formally designate as lunar dust. These particles are not rounded, they are fractured and angular, with edges and surfaces that under electron microscopy resemble shards of shattered glass rather than grains of ordinary sand. Their geometry is sharp enough to cut biological tissue at the cellular scale, but the geometry is only one dimension of the problem. The Moon's surface is continuously subjected to the solar wind, a stream of energetic charged particles radiating outward from the Sun. This bombardment implants ions into the outer surfaces of regolith grains and strips electrons from their atomic structures, leaving the particles in a state of persistent electrostatic charge. On Earth, atmospheric humidity dissipates electrostatic charge almost immediately. On the Moon, there is no humidity, and the charge accumulates indefinitely. Electrostatically charged dust clings to any surface it contacts: metal, glass, fabric, polymer coatings, with a tenacity that mechanical brushing cannot overcome. Apollo crews brushed their suits before re-entering the lunar module. The effort removed perhaps half the visible material, the rest held fast. The chemical character of regolith introduces yet another layer of danger. Lunar soil is composed of roughly 50% silicon dioxide by mass, with iron oxides and calcium compounds making up most of the remainder. But these minerals are not inert in the way that weathered terrestrial minerals are. The fracturing process that creates fine dust also exposes fresh mineral surfaces that have never interacted with oxygen or liquid water. These freshly exposed surfaces are chemically reactive. When they encounter moisture, as they inevitably would inside a pressurized habitat containing breathing, perspiring human beings, they can produce free radicals. These are highly reactive molecular fragments that cause direct damage to biological tissue at the cellular level. Laboratory research using lunar simulant dust has demonstrated that sustained exposure destroys lung cells and neurons. The particles are fine enough to penetrate past the body's natural filtering mechanisms and lodge deep in the alveoli, where gas exchange takes place. Once embedded, they cannot be expelled. Their geometry and chemical reactivity drive chronic inflammation. What prolonged inhalation of actual lunar dust would do to a human being over months or years of continuous low-level exposure remains genuinely unknown, because no person has ever been exposed for that duration. The data from Apollo, from laboratory simulant studies, and from terrestrial research on fine silicate dust exposure suggests the risk is not theoretical. NASA has been funding dust mitigation research for years, and some of it has produced genuine results. The electromagnetic dust shield, which uses oscillating electric fields to lift and repel charged particles from surfaces, was successfully demonstrated on the actual lunar surface in March 2025 aboard a small experimental unit delivered by a commercial lander. The shield cleared dust from glass and radiator panel surfaces with encouraging effectiveness. It is a genuine step forward, but it is a narrow one. The electromagnetic shield protects flat exposed surfaces. It does not protect the moving joints of spacesuits. It does not prevent particles from entering airlocks during crew transitions. It does not keep regolith out of habitat ventilation systems or stop fine material from grinding against mechanical seals across thousands of operational cycles. It is one instrument in a fight that is taking place everywhere simultaneously. The operational reality of dust management at a permanently occupied base would look something like this. Every time a crew member exits the habitat for a surface excursion, they pass through an airlock. Dust enters the airlock during that transition. When the crew member returns, they attempt to clean themselves and their equipment before the inner door is opened and the volume is repressurized. Some dust always remains. It enters the habitat. The ventilation system must filter it continuously, using filter media that itself degrades under abrasive loading and must be replaced at intervals with components that can only come from Earth or be manufactured locally. Every piece of surface equipment, rovers, drilling systems, sample collection tools, construction machinery, accumulates dust on every mechanical interface. Bearings wear faster, optical sensors cloud over time. Electrical connectors develop increasing resistance as regolith particles work their way into contact surfaces. Each system demands inspection and maintenance at intervals shorter than any designer would accept under terrestrial conditions. Dust management would consume a substantial portion of available crew time every single day, not on designated maintenance days. Every day, the Moon does not pause its production of electrostatically charged, chemically reactive, physically abrasive particles, and the dust is continuously replenished. Every footstep kicks up particles that, in the 1/6 gravity environment and hard vacuum, travel far higher and settle far more slowly than intuition would suggest. Vehicle traffic raises plumes capable of traveling kilometers before settling. Even without human activity, differential electrostatic charging near the boundary between sunlit and shadowed terrain causes fine particles to spontaneously levitate, rising above the surface on electric field gradients strong enough to lift them against the Moon's gravity. A base operating near this terminator environment, exactly where South Pole installations would sit given the perpetually low sun angles, would face continuous background dust mobilization as a feature of its location rather than a consequence of its operations. There is no solving the dust problem. There is only managing it. The management is permanent, it is demanding, and it never ends for as long as the base remains occupied. The second enemy wages its war through a mechanism that sounds almost too simple to be catastrophic. It does not strike suddenly, it does not announce itself, it works quietly, cycling through the same motion over and over, each repetition slightly weaker than the last, each transition leaving behind damage so small it is invisible to the naked eye, but so cumulative that after hundreds of cycles it becomes structural failure. The mechanism is thermal cycling, and on the lunar surface, it operates with a consistency and severity that no material or machine built for human use has ever been designed to withstand indefinitely. We've already described what the raw temperatures look like at the South Pole. Sunlit surfaces climbing above 100 degrees Celsius, shadowed areas nearby falling below -70, permanently shadowed crater floors approaching -230. But raw temperature extremes, as severe as they are, tell only part of the story. The part that engineers lose sleep over is not the temperature itself. It is the rate and regularity of the transitions between extremes. On Earth, even in harsh climates, atmospheric gases moderate temperature shifts. A surface losing direct sunlight does not immediately plunge toward the coldest possible temperature. Air surrounds it, carries residual warmth, slows the drop. A surface gaining sunlight in the morning does not instantly rocket to its maximum temperature. Atmospheric absorption and thermal mass in the surrounding medium buffer the change. On the Moon, none of this buffering exists. A surface moving from direct solar illumination into shadow, or having shadow sweep across it as the sun traces its slow, shallow arc along the southern horizon, begins changing temperature almost immediately and continues changing until it equilibrates with its new, radiative environment. That equilibration can represent a shift of 150 degrees or more, and it can begin within minutes of the transition. Every material subjected to this kind of cycling expands when heated and contracts when cooled. This is elementary physics. What makes it dangerous is that different materials expand and contract at different rates, a property called the coefficient of thermal expansion. a structure built from multiple materials, which every habitat module and every piece of surface equipment necessarily is, experiences differential movement at every joint, every fastener, every interface between dissimilar components. A joint that fits precisely at 20 degrees Celsius develops microscopic gaps at -150. A seal that holds at operating temperature loses its compression at the cold extreme. A weld that passed inspection under terrestrial conditions begins propagating a fatigue crack after 50 thermal cycles. After 500 cycles, the crack has grown. After 5,000, it may reach a critical length. This is not speculation. It is the documented primary failure mechanism for long-duration hardware operating in space, and it is one of the central reasons why spacecraft designers obsess over material selection in ways that seem excessive until you understand the environment those materials must survive. On the International Space Station, thermal cycling is already a significant and ongoing maintenance concern. The station orbits Earth approximately every 90 minutes, cycling between sunlight and shadow 16 times per day. Despite operating in an environment where the thermal range is considerably smaller than the lunar surface, and where the station's large thermal mass moderates transitions, components throughout the structure require regular inspection for fatigue, cracking, and replacement of thermally stressed seals and gaskets is a routine maintenance activity. On the lunar surface at the South Pole, the cycling period depends entirely on local topography. Sites on broad, elevated plateaus may experience relatively slow cycles as the sun traces its low arc. Sites near the edges of ridgelines, where local terrain features create abrupt transitions between full illumination and deep shadow, may experience far more rapid swings as the sun dips behind a nearby peak and re-emerges, cycling a stationary piece of equipment through a 100-degree temperature change in the span of minutes rather than hours. Equipment deployed at these sites could accumulate thousands of individual thermal shock events per year, each one flexing joints, each one propagating existing cracks slightly further, each one stressing seals that are simultaneously being ground down by dust and degraded by radiation. The absence of convective cooling creates a thermal management challenge that is easy to underestimate if your engineering intuition was formed in an atmosphere. On Earth, cooling a heat-generating system, an electronics rack, a motor, a power converter is a routine engineering task. You move air across it. You add fins to increase surface area. You use a fan. In vacuum, none of these approaches work. Heat cannot be transferred through a medium that does not exist. Outside a pressurized volume, the only mechanisms available are radiation outward towards space and conduction downward into the regolith. Radiation requires large surface area oriented toward empty sky. Conduction into regolith is inefficient because lunar soil is a remarkably poor thermal conductor, owing to its particulate structure and the vacuum gaps between grains. Cooling a habitat or a power system on the moon, therefore, requires dedicated radiator panels, typically flat or tubular structures, through which a working fluid circulates, carrying heat from internal systems out to surfaces that can radiate it away. These radiator panels must be large enough to reject the required thermal load. They must be oriented correctly relative to the sun and the habitat to function efficiently. And they must survive the same surface environment as every other external component. Dust accumulates on radiator surfaces just as it accumulates on solar panels. A radiator panel coated in a thin layer of regolith radiates less efficiently because the dust changes the surface emissivity, the property that determines how readily a surface releases thermal energy. As dust loading increases, radiator efficiency falls. As radiator efficiency falls, internal temperatures rise. As internal temperatures rise, electronics approach their thermal limits and mechanical systems experience additional stress. Maintaining radiator performance requires regular dust removal from panel surfaces. Dust removal requires crew time and potentially surface excursions that themselves introduce dust into the habitat through airlock cycling. The thermal management system generates a maintenance demand that feeds directly back into the dust problem. The two are inseparable. Heating during shadow periods presents the mirror image challenge. When a South Pole site enters a multi-day shadow period, every surface begins radiating its stored thermal energy into space with no solar input to replace it. Temperatures fall. Batteries lose a significant fraction of their usable capacity in extreme cold because the electrochemical reactions that store and release energy in lithium-based cells slow dramatically at low temperatures. Lubricants that performed adequately at operating temperature thicken and eventually approach solidification. Electronics can fail as solder joints contract beyond their tolerance and circuit board substrate materials become brittle. Mechanical actuators require higher driving forces to overcome increased fluid viscosity and stiffened elastomers. Keeping a habitat and all its supporting external equipment warm enough to function through several Earth days of continuous darkness requires sustained power for electric heating systems. That power cannot come from solar panels during a shadow period. It must come from stored energy or an alternative generation source. This requirement feeds directly into what may be the most technically demanding problem the entire base must solve, and it connects the thermal problem inextricably to the fourth great enemy, which we will reach. But first, the third. Vacuum is the condition that transforms every other challenge on the Moon from difficult to potentially lethal. Dust is unpleasant and damaging in an atmosphere. Temperature extremes stress materials in any environment. Radiation reaches the surface more intensely without atmospheric shielding, but in each case, an atmosphere provides partial mitigation. Vacuum removes every mitigation simultaneously. It is not merely the absence of air. It is the absence of the medium through which almost every engineering solution for environmental hazards was developed. A pressurized habitat on the lunar surface must maintain approximately 1 standard atmosphere of internal pressure against the external vacuum. In physical terms, this means a pressure differential of roughly 100 kilopascals pushing outward across every square meter of the habitat wall. For a modest cylindrical module 4 meters in diameter, the total outward force on a single end cap exceeds 500,000 newtons. The structure must bear this load without interruption for as long as the base is occupied, while simultaneously surviving thermal cycling that flexes every joint, dust abrasion that works at every seal surface, and radiation that degrades the mechanical properties of composite materials and polymer components, and the vibration generated by internal machinery and crew activity. Modern material science can build structures capable of meeting these demands, but capable of meeting them is different from meeting them indefinitely without maintenance, inspection, and component replacement. The critical vulnerability in any pressure-containing structure is not the wall itself but the penetrations through it. Habitats require airlocks, they require windows, they require docking interfaces for visiting vehicles, they require cable pass-throughs for power and communications. They require equipment hatches for accessing external systems. Each of these features is a designed interruption in the pressure envelope, and each one is a location where the structural integrity of the habitat depends on a seal rather than solid material. The operational history of the International Space Station provides the most relevant data set available for understanding what pressure seals actually do under extended service in space, and the record is instructive. The station has experienced multiple slow leak events, requiring sustained diagnostic effort to locate and resolve. One particularly significant case involved the Zvezda service module, where a slow leak was identified in 2019, and the crew spent considerable time attempting to pinpoint its location. The source was eventually traced to a crack in an internal transfer tunnel. Subsequent inspection revealed additional cracks requiring further remediation. The crew devoted hundreds of combined hours to managing this single leak across months of diagnostic and repair work. During that entire period, the station was operating in microgravity, where mechanical stress on seals is lower than it would be on a surface installation, where no dust intrudes into seal interfaces, and where no thermal cycling of the severity experienced on the lunar surface occurs. On the Moon, those conditions are reversed on every count. Dust works into seal surfaces during every airlock cycle. Thermal contraction opens microscopic gaps in seal housings during cold periods. Radiation degrades the elastomeric materials from which seals are manufactured. and airlocks cycle with a frequency that no space station module has ever experienced. A 4-person crew performing regular surface excursions for scientific work, external maintenance, and construction activities might cycle the primary airlock 8 to 10 times per day. That is 3,000 or more cycles per year. Each cycle imposes a pressure differential load across the seal as the volume is evacuated or repressurized. Each cycle allows a small quantity of dust to contact the seal surface. Each cycle occurs against a background of thermal stress that may be actively changing the geometry of the seal housing in real time. No airlock seal in the history of human space exploration has been tested under the combined conditions of this frequency, this dust environment, this thermal cycling range, and this radiation exposure over durations measured in years. The expected service life of these components under actual lunar operational conditions is an open engineering question. The answer determines how large a seal inventory the base must maintain, how frequently crew members must perform the demanding and time-consuming task of replacing a pressure-critical interface, and how much of the already strained crew schedule must be allocated to seal management alone. Beyond the direct, lethal risk of decompression, vacuum creates slower-acting threats that are no less serious for being gradual. The first is outgassing. Materials exposed to vacuum in the absence of atmospheric pressure lose volatile molecular components to the surrounding void. Lubricants are particularly vulnerable. On Earth, lubricants are formulated to function in atmospheric conditions where oxygen and moisture actually contribute to maintaining their working properties. In vacuum, the volatile organic compounds that give lubricants their viscosity, their film-forming behavior, and their ability to prevent metal-on-metal contact escape molecule by molecule into the surrounding emptiness. The lubricant gradually thickens, loses its film-forming capacity, and eventually ceases to provide meaningful protection to the surfaces it was meant to separate. Aerospace-grade vacuum lubricants exist and have been developed specifically for this environment. They outgas more slowly, they maintain their properties across wider temperature ranges than commercial alternatives. But they still degrade. They still have finite service lives in vacuum. A rover drive joint, lubricated at the beginning of a mission, performs smoothly for the first weeks. By the 6th month, as outgassing has progressed and dust contamination has worked through protective seals, the joint requires more driving force. By the 12th month, bearing surfaces may be showing measurable wear. Replacing the lubricant in a joint on the lunar surface requires an extravehicular activity. That means suiting up, cycling through the airlock, working on the external mechanism with gloved hands in vacuum, reversing the process on return, and managing the dust that has inevitably entered the airlock during the operation. A maintenance task that would require perhaps 20 minutes in a terrestrial workshop consumes the better part of a working day on the Moon, competes with every other maintenance demand for crew time, and generates its own secondary costs in suit wear, airlock cycling, and dust ingress. Polymers degrade under sustained exposure to vacuum, combined with ultraviolet radiation and charged particle bombardment. This matters enormously because polymers are ubiquitous in habitat construction. The seals and gaskets throughout a pressurized module are polymer-based. The insulation on electrical cables is polymer-based. Window coatings, flexible connectors between structural elements, protective outer layers on composite pressure walls, all rely on polymer materials that were qualified under terrestrial conditions or under the comparatively gentler environment of low Earth orbit. Under the combined assault of lunar surface vacuum, intense ultraviolet flux from an unfiltered sun, continuous charged particle bombardment, and thermal cycling of hundreds of degrees, these materials undergo embrittlement. They lose the flexibility that allows them to maintain contact pressure against mating surfaces. They develop microcracks that propagate under cyclic loading. Laboratory testing using simulated lunar surface conditions has demonstrated measurable embrittlement in standard aerospace polymers within months of exposure. A base expected to operate for years must treat every polymer component in its system as existing on a degradation timeline that ticks faster than any Earth-based qualification program would suggest. The final vacuum-specific failure mode is one that surprises people who have not encountered it before: cold welding. In Earth's atmosphere, the surfaces of metals are covered with thin oxide layers that form almost instantly when bare metal is exposed to oxygen. These oxide layers are chemically distinct from the underlying metal. They prevent direct atomic contact between metal surfaces, even when those surfaces are pressed together under load. This is why mechanical components made of the same metal can be assembled, disassembled, and reassembled without fusing to one another. In vacuum, no oxygen is present, no oxide layers form. When two clean metal surfaces are pressed into contact in vacuum, the atoms at each surface can form direct metallic bonds across the interface, effectively welding the components together without any heat or additional material. Cold welding has caused mechanism failures on deployed space hardware. Multiple satellite solar array deployment systems experienced bonding between metallic hinge components after extended storage in vacuum, requiring engineers to redesign contact surfaces with anti-galling coatings specifically for subsequent missions. On a lunar base, the surfaces subject to this risk include airlock hinge mechanisms, rover joint components, drill interfaces, construction equipment articulation points, and any other mechanical system where two metal surfaces contact each other repeatedly. Every such interface must be designed with materials selected to resist cold welding or coated with anti-galling treatments that themselves degrade over time and must eventually be renewed. Every renewal is another maintenance task, another draw on crew time, another entry in the spare parts manifest that must be delivered from Earth. Dust, thermal cycling, and vacuum do not operate sequentially. They operate simultaneously, and they reinforce each other. Thermal cycling opens microscopic gaps that dust enters. Dust contaminates seal surfaces that vacuum then exploits as leak paths. Vacuum outgases, lubricants that thermal cycling has already stressed and into which dust has already worked. The three combine to accelerate degradation in every mechanical system faster than any individual threat would manage alone. And this compounding does not plateau. It accelerates. A system that shows only minor wear in its first 3 months may show dramatically increased degradation by month 9, as the accumulated effects of thousands of thermal cycles, months of dust infiltration, and continuous outgassing begin to interact with each other in ways that the early degradation rate did not predict. Engineers call this behavior nonlinear accumulation, and it is one of the most dangerous characteristics of long-duration operations in severe environments. The rate of degradation you observe early in a mission is not the rate you can project forward. The true rate grows, and it grows in a way that makes the second year of a permanent lunar base significantly harder to sustain than the first. Which brings us to the fourth enemy, the one that everything else depends on: power. Without continuous, reliable electrical power at sufficient capacity, nothing else the base does matters. The habitat cannot maintain its internal pressure without the pumps and monitoring systems that manage atmospheric quality. The thermal management system cannot circulate coolant through its radiators or run heaters through shadow periods. The dust mitigation systems cannot operate. The air revitalization equipment stops processing carbon dioxide. The water recycling system shuts down. Communications cease. Life support fails. Power on the moon is not infrastructure. It is the prerequisite for survival. Losing it is not an inconvenience to be managed while a utility company dispatches a repair crew. Losing it initiates a countdown measured in hours before the habitat becomes uninhabitable. The margin is absolute, and there is no external rescue available within any useful timeframe. NASA's selection of South Pole sites was driven substantially by power considerations. The elevated terrain near Shackleton Crater and adjacent formations receives sunlight for approximately 80 to 90% of the lunar year. This is the best solar resource available anywhere on the moon. Equatorial sites, by comparison, experience a 2-week lunar night, during which solar power is completely unavailable, making sustained habitation without nuclear power essentially impossible. The South Pole's near-continuous illumination represents a genuine advantage for solar generation. But 80 to 90% is not 100. Shadow periods occur, and during those periods, A base relying on solar power must survive entirely on stored energy or alternative generation. The arithmetic of energy storage for lunar shadow survival has been described by researchers working on this specific problem as perhaps the most demanding energy storage challenge anywhere in solar system exploration. Understanding why requires working through the numbers with some care. A minimal 4-person lunar base providing life support, thermal management, lighting, communications, and essential equipment operation requires continuous electrical power, estimated conservatively at 25 to 30 kilowatts. Analyses that include active thermal management for external equipment and initial resource extraction operations push this figure towards 65 kilowatts. Using the lower figure, surviving a shadow period of 4 Earth days requires storing 2,400 kilowatt-hours of electrical energy. The best lithium-ion batteries currently qualified for space applications store approximately 200 watt-hours per kilogram at the individual cell level. At the system level, accounting for the structural packaging, thermal management provisions, charge regulation hardware, and safety margins that a space-rated battery assembly requires, the usable energy density falls to something closer to 150 watt-hours per kilogram. Storing 2,400 kilowatt-hours at that density requires 16,000 kilograms of batteries, 16 metric tons, approximately the total payload capacity of an entire large lunar lander devoted to nothing but batteries for a single shadow survival event. And that calculation assumes the batteries perform at their rated capacity. In the extreme cold of a lunar shadow period, lithium-ion cells lose 30 to 50% of their output capacity unless actively heated. Active heating consumes power from the reserves the batteries are supposed to provide, reducing the effective storage further. The numbers do not close without supplemental generation. This is why nuclear power is not an optional enhancement to the moon base plan. It is a structural necessity. Without a generation source that operates independently of sunlight, a permanent South Pole base cannot reliably survive its own shadow periods. NASA's phased plan explicitly includes nuclear power development, radioisotope thermoelectric generators, which convert the thermal energy from decaying radioactive material into electricity, can provide hundreds of watts of reliable continuous power and have operated in deep space for decades. But hundreds of watts is insufficient for a crewed base requiring tens of kilowatts. The ultimate solution is a compact fission reactor. NASA and the Department of Energy have been jointly developing exactly this capability. The Kilopower reactor program and its successor development efforts have been working toward a surface fission system capable of producing at least 10 kilowatts of electrical power. The technology is within reach of current engineering capability. But a surface fission reactor introduces its own set of constraints that the press conference imagery consistently fails to show. The reactor requires an exclusion zone around its installation site. With adequate regolith shielding piled around the reactor body, analyses suggest this zone can be reduced to approximately 90 meters. 90 meters is a significant distance on a base whose usable ridgeline terrain may be only a few hundred meters wide. Every other asset in the base must be positioned in relation to this exclusion boundary. Habitats cannot be within it. Crew pathways between the habitat and external work areas must route around it. Power cables must traverse the distance from reactor to base, running across terrain subject to all the thermal cycling and dust contamination affecting every other external system. The reactor must be cooled. In vacuum, that means radiator panels subject to the same dust accumulation, micrometeorite erosion, and thermal cycling that degrades every other external radiator in the system. If reactor cooling efficiency falls because dust has settled on the radiator surfaces, the reactor must reduce output or risk thermal damage to its core components. Maintaining reactor cooling performance, therefore, joins the already extensive list of external maintenance tasks requiring crew attention and surface excursion time, and the reactor represents, in its initial deployment, a single point of catastrophic failure. If the reactor fails during a shadow period when solar generation is unavailable, the base faces a life support crisis with no immediate alternative power source. This forces the base to maintain backup energy storage, capable of sustaining the crew through the time required to restore reactor operation or to wait for sunlight to return. That backup storage requirement partially negates the reactor's advantage, because it means the base still carries substantial battery mass as a contingency, even after the reactor is operational. Launching a nuclear reactor to the lunar surface also requires regulatory approval, international notification under relevant space treaties, and a level of public and political acceptance that cannot be taken as guaranteed. The history of nuclear material launches in space includes both successes and periods of intense public scrutiny. A compact fission reactor represents a more technically complex and politically visible step than any previous nuclear space mission. Delays in the approval process could push nuclear power availability past the dates that the base's construction timeline requires, forcing the base to operate for longer than planned on a solar and battery architecture that its designers know is insufficient for long-term permanent occupation. The power system, like every other system on the Moon, does not exist in isolation. It depends on functioning radiators, which depend on dust management, which depends on crew time, which depends on the crew being fed and healthy, which depends on life support, which depends on power. Every thread in this web leads back to every other thread. Pull on any one of them, and the tension propagates through the entire system. This is the character of the lunar environment as an engineering problem, not a single large difficulty to be solved once and left behind. A web of interdependent challenges, each feeding the others, each generating new demands on resources that are already fully committed elsewhere. And the weight of this web does not remain constant. It increases with time. As every system accumulates wear, as every seal degrades, as every lubricant thins, as every filter loads with particles, as every crew member's body absorbs another day's worth of radiation, the Moon does not let anything rest. It works on everything always, and the longer a base has existed, the harder it is to keep running. The 4 enemies described so far are the visible ones. You can see dust accumulating on a visor. You can measure a temperature swing with an instrument. You can watch a pressure gauge begin its slow decline during a leak. You can read a power budget and see the numbers failing to balance. These are threats that manifest in hardware, in equipment, in the physical systems that engineers can design around, test against, and at least partially mitigate with sufficient ingenuity and resources. What comes next is different. These threats work in silence. They accumulate without announcing themselves. They operate inside human tissue, inside fatigue cracks too fine to detect without specialized instruments, inside logistics spreadsheets where a single missing line item cascades through the entire supply chain. They are the threats that emerge only when habitation extends beyond any duration humanity has ever sustained on the lunar surface. And they are the threats that transform a moon base from an extraordinarily difficult engineering project into something closer to a permanent emergency that never fully resolves. The first of them never stops. Radiation on the Moon is not an event you prepare for and then recover from. It is not a storm that passes or a hazard that can be switched off. It is the permanent condition of the environment, operating continuously at a rate that accumulates inside every cell of every person living there, every hour of every day, for the entire duration of their stay. On Earth, the average person absorbs roughly 2 to 3 millisieverts of radiation per year from natural background sources, including trace radioactive elements in soil and building materials, cosmic rays filtered through the atmosphere, and medical imaging. Airline pilots and cabin crew, who spend their working lives at altitudes where atmospheric shielding is thinner, accumulate perhaps 5 to 6 millisieverts annually. Astronauts aboard the International Space Station, partially protected by Earth's magnetic field and operating within the residual shielding of low Earth orbit, receive between 150 and 200 millisieverts per year. On the unshielded lunar surface, the continuous dose from galactic cosmic radiation alone reaches approximately 400 millisieverts per year. That figure is not derived from models. It comes from direct, physical measurement. China's Chang'e 4 lander carried a radiation dosimeter to the surface in 2019 and operated it through 2020, recording the first ground truth data on lunar surface radiation exposure ever obtained. The measurements confirmed what theoretical calculations had long predicted. The dose rate is approximately 2 to 3 times what ISS crew members experience in orbit. 400 millisieverts per year is a number that requires careful framing. It does not cause immediate symptoms. Acute radiation syndrome, the condition associated with sudden high-dose exposure, does not manifest until a dose above roughly 700 millisieverts is delivered within a short period, typically hours to days. The galactic cosmic ray dose arrives at a continuous rate of approximately 46 microsieverts per hour. A person on the lunar surface does not feel it. They do not experience nausea, fatigue, or any other immediate indicator. The damage accumulates invisibly at the molecular level, in the DNA of dividing cells, in the crystalline structures of the eye lens, in the myelin sheaths of nerve fibers, in the walls of blood vessels. At 400 millisieverts per year, an astronaut stationed continuously on the lunar surface for 18 months would accumulate 600 millisieverts of total exposure. NASA's career dose limit for astronauts is 600 millisieverts lifetime. A single 18-month rotation would consume the entire career allowance of any crew member who participated. Either the dose limits must be revised upward, accepting higher long-term cancer risk, or crew rotations must be kept short enough that individual exposures remain below the limit, which means more frequent crew exchanges, more launches, more transit missions, and more cost. Neither option is without consequence. The biological effects of this chronic exposure are not speculative. They are documented outcomes from decades of epidemiological research on radiation-exposed populations and from controlled laboratory experiments using particle accelerators that replicate the galactic cosmic ray spectrum. Elevated cancer risk across multiple organ systems. Increased probability of cataract formation in the eye lens. Potential degeneration in the central nervous system, including impairment of cognitive function and memory. Accelerated cardiovascular disease. Possible heritable effects in germ cells. These outcomes are probability increases, not certainties. Not every exposed person develops every consequence, but the probability increases are real, measurable, and they scale with cumulative dose. The predictable component of the radiation environment, the steady galactic cosmic ray background, is the one that can be planned around. The dangerous component is the one that cannot. Solar particle events occur when the sun ejects massive quantities of energetic protons during solar flares or coronal mass ejections. These events are irregular and sporadic. Forecasting capability has improved substantially over the past 2 decades, with satellite-based solar monitoring systems now providing warning times of roughly 15 minutes to a few hours before the energetic particle front arrives at the moon. But the warning time is short, and the intensity of individual events spans an enormous range. A modest solar particle event might deliver a supplemental dose equivalent to a few additional days of galactic cosmic ray exposure. An extreme event could deliver several sieverts to an unshielded person within hours. Several sieverts is a lethal dose. This is not a theoretical edge case constructed to illustrate a point. In August of 1972, between the Apollo 16 and Apollo 17 missions, the Sun produced one of the largest solar particle events recorded in the instrumental era. Had any Apollo crew been conducting surface operations during that event rather than safely on Earth, they would almost certainly have received a fatal radiation dose within hours. The event was so intense that even the radiation shielding of a lunar module, which provides far less protection than a purpose-built shelter, would have been inadequate. The timing was fortunate. The consequences of slightly different timing would have been catastrophic. A permanent base cannot rely on fortunate timing across years of continuous occupation. It must have dedicated radiation shelter capability that every crew member can access within minutes of receiving an event warning. The shelter must provide enough shielding mass to reduce the dose from a worst-case solar particle event to survivable levels while the event passes, which typically takes hours to perhaps a day for the most intense events. How much shielding is required? Most technical analyses converge on approximately 80 centimeters of lunar regolith, or an equivalent mass of alternative shielding material, as the minimum necessary to attenuate the most dangerous proton energies in a large event to below acutely lethal levels. 80 centimeters of regolith also significantly reduces the chronic galactic cosmic ray dose rate inside the shelter, though it cannot eliminate it entirely. The highest energy galactic cosmic ray particles can penetrate meters of solid material, and no practical shielding mass can stop them completely. Providing 80 centimeters of regolith coverage over an inhabited structure requires either excavating a cavity in the lunar surface and constructing the habitat below grade, which demands heavy excavation equipment capable of operating reliably in vacuum, thermal extremes, and pervasive, abrasive dust, or piling regolith on top of a surface habitat after it has been landed and positioned, which requires moving tens to hundreds of metric tons of material using machinery that is itself subject to every degradation mechanism the surface imposes. Both approaches are physically achievable. Neither has been demonstrated at any useful scale on the lunar surface. Both require construction equipment that must be launched from Earth, landed without damage, deployed, commissioned, and maintained before it can perform a single hour of productive work. There is an additional radiation hazard at the lunar surface that receives less attention in public discussions but is taken seriously in the technical literature. When high-energy galactic cosmic ray particles strike the regolith, they initiate nuclear reactions in the soil that produce secondary radiation, primarily fast neutrons and gamma rays. This secondary radiation scatters in all directions from the impact point, including upward and sideways. A habitat sitting on the surface therefore receives radiation not only from the sky above, but from the ground below and the soil surrounding it. Shielding the roof and walls while leaving the floor unprotected is insufficient. The floor must also be addressed, either by adding shielding mass beneath the habitat structure, by elevating the habitat on a platform that provides clearance above the surface, or by accepting an elevated dose contribution from below. The secondary neutron environment varies with regolith composition, which is not uniform across the South Pole region. Local variations in iron, titanium, and hydrogen content affect how efficiently the soil produces and moderates secondary neutrons. Characterizing this environment at specific candidate base sites is one of the tasks the Phase 1 robotic precursor missions must accomplish before any crewed infrastructure is committed to a location. Radiation also degrades hardware. This is sometimes treated as a secondary concern beneath the human health risk, but it is operationally significant in its own right. Polymer materials throughout the habitat, including the seals, gaskets, cable insulation, and flexible structural elements already stressed by thermal cycling and vacuum exposure, experience accelerated embrittlement under sustained, charged particle bombardment. Solar panel efficiency decreases as radiation progressively damages the crystalline structure of photovoltaic cells, reducing their ability to convert solar energy into electricity even when their surfaces are clean. Electronics throughout every system can experience single-event upsets, events in which a high-energy particle strikes a transistor, flips a stored bit, and causes either a software error or a permanent hardware fault. Radiation-hardened electronics designed specifically to resist these effects exist and have extensive flight heritage, but they carry significant penalties. They are heavier than equivalent commercial components. They are more expensive. They are typically less capable in terms of processing speed and memory density. And they are often based on older semiconductor processes because radiation hardening requires design and manufacturing choices that are incompatible with the aggressive scaling that drives commercial electronics performance. A base that uses fully radiation-hardened electronics throughout gains robustness at the cost of mass, expense, and reduced computational capability. A base that uses commercial components to save mass and cost accepts higher rates of radiation-induced failure and must carry additional spare electronics to replace damaged units. Either path imposes penalties that compound across the total system budget. Now consider what is happening to the human body during all of this. Not just from radiation, but from the totality of the lunar environment acting on biological systems that evolved over millions of years in full Earth gravity, in an atmosphere, on a world where every physical intuition about how things work was formed. The Moon's gravitational acceleration is approximately 1/6 that of Earth. This partial gravity environment is the great unknown of human space medicine. Decades of research conducted aboard the International Space Station have produced a detailed and well-validated picture of what happens to human physiology in the near weightlessness of low Earth orbit. Bone mineral density decreases at a rate of approximately 1 to 2% per month in weight-bearing skeletal regions, concentrated in the lumbar spine, the pelvis, and the lower limbs. Skeletal muscle mass declines despite structured exercise protocols, with particular losses in the postural muscles of the back and legs. The cardiovascular system reorganizes as the heart no longer needs to generate sufficient pressure to pump blood upward against full gravitational loading. Cardiac muscle atrophies. The fluid distribution throughout the body shifts toward the head, increasing intracranial pressure. In a substantial fraction of long-duration ISS crew members, this elevated intracranial pressure causes measurable changes to the optic nerve and the shape of the eyeball, impairing visual acuity in a condition now formally designated spaceflight-associated neuroocular syndrome. The immune system shows suppression across multiple measured parameters. Wound healing slows. The composition of the gut microbiome shifts in ways that are not yet fully understood. All of these effects have been documented, quantified, and partially mitigated by rigorous onboard exercise protocols that occupy approximately 2 hours of every crew member's day aboard the station. The exercise cannot eliminate the effects. It can slow them enough to keep crew members functional for 6-month rotations and allow recovery after return to Earth. The critical and unanswered question for a lunar base is whether 1/6 gravity is enough to prevent these changes, slow them to a clinically acceptable rate, or whether it merely delays them at a rate that still becomes dangerous over stays measured in many months. The honest answer, supported by every space medicine specialist who has publicly addressed this question, is that no one knows. No human being has ever spent more than 3 days in 1/6 gravity. Every data point in the entire field of human space physiology comes from either full Earth gravity or the near weightlessness of orbital spaceflight. The partial gravity regime in which the Moon sits is a complete medical blank. There is no data. There are models, extrapolations, and informed hypotheses. There is no evidence. The mechanical loading on bones in 1/6 gravity is approximately 1/6 of what those bones experience during normal activity on Earth. Whether this reduced loading is sufficient to maintain the cellular processes that continuously remodel and strengthen bone tissue is genuinely uncertain. If it is not, if lunar gravity proves insufficient to halt the bone loss documented in microgravity, crew members will be losing bone density throughout their entire stay, and arriving back on Earth after months or years weaker than when they left, at elevated risk of fracture, and potentially requiring extended rehabilitation before they can function normally again. If the loss rate in lunar gravity is slower than in microgravity, but still significant, longer rotations become more medically problematic than shorter ones, limiting how long any individual crew member can serve before needing to return to Earth for recovery. This uncertainty has direct consequences for base design. If 1/6 gravity proves insufficient to maintain crew health across multi-month stays, countermeasures must be incorporated. Centrifuge systems that spin crew members to generate artificial gravitational loading are the most frequently proposed solution. These devices can be engineered to fit within a habitat module. They add mass, consume volume, require power, and generate mechanical vibration that propagates through the habitat structure. Their operational use adds further demands on crew time that already cannot accommodate everything required of it. Psychological health compounds every physiological burden. The Apollo astronauts spent 72 hours on the surface at most, buoyed by the extraordinary experience of being the first human beings to walk on another world, in constant contact with mission control, and with the full knowledge that they would be home within a week. International Space Station crew members endure 6 months in confinement, but they communicate with family in real time, receive periodic resupply missions that bring personal items and fresh food, and have the visual and psychological anchor of Earth filling their windows in familiar blue and white. A lunar base crew would face conditions qualitatively different from both of these reference points. Confinement within a small, pressurized volume for months at a time, physically demanding and relentlessly repetitive maintenance work performed in an environment where the consequences of a single error can be lethal. Earth visible only as a small, brilliant disk in the black sky, close enough to see but requiring 3 days of spaceflight to reach. Communication with family and friends subject to only a 1.5-second round-trip delay, which is technically manageable but psychologically colored by the knowledge that help, if needed, cannot arrive for days at minimum. Shadow periods that eliminate solar power and raise the stakes, the steady background awareness that the environment outside the habitat walls is actively working to compromise those walls every hour. Research on analogous extreme environments, Antarctic winter overstations, nuclear submarine deployments, isolated polar research postings, documents a consistent pattern of psychological effects that intensify with duration. Depression rates increase. Interpersonal conflict within small isolated groups escalates in frequency and severity. Sleep quality degrades as circadian rhythms lose their normal environmental anchors. Cognitive performance, particularly on tasks requiring sustained attention and novel problem-solving, declines under chronic stress and sleep disruption. These effects have been observed in people who are living in conditions considerably more forgiving than a lunar base, with breathable air freely available, no life-threatening vacuum on the other side of their walls, and at least the theoretical possibility of emergency extraction. The compounding of biological threats creates a situation that is qualitatively different from the sum of its parts. A crew member who is accumulating radiation dose, losing bone mineral density at an uncertain rate, breathing trace quantities of regolith dust that escaped filtration, experiencing disrupted sleep from confinement and psychological stress, and spending 2 hours daily on mandatory exercise to slow their physical deconditioning is not functioning at their baseline capability. Their cognitive performance is degraded by some margin. Their physical capability is diminished by some amount. Their tolerance for additional stresses is reduced, and they are the person responsible for maintaining the complex life support system that is keeping everyone alive. The base does not merely need to sustain human life in a minimal biological sense. It needs to sustain human performance at the level required to keep a highly complex and continuously degrading installation functioning. If crew effectiveness falls faster than anticipated, the maintenance burden that was already at the limit of what 4 to 6 people can manage becomes impossible to service. Systems begin failing faster than they can be repaired. The base enters a deteriorating spiral where declining crew capability and accelerating system degradation reinforce each other, which leads directly to the maintenance problem. And the maintenance problem on a permanently occupied lunar base is not a challenge to be solved at the beginning and then left behind. It is the central operational reality of every single day the base exists. Every mechanical system ever built has a designed operational life. That life is defined under specific conditions of temperature, pressure, chemical environment, loading frequency, and exposure. When those conditions are exceeded, operational life shortens. When multiple conditions are simultaneously exceeded, the shortening is not additive, it is multiplicative. The failures come earlier than the design predicted. They come from combinations of mechanisms that individual component tests did not anticipate, and they come at a rate that accelerates as the system ages. The International Space Station is the closest available reference for understanding long-duration life support maintenance demands, and its history is sobering even for those familiar with it. The station's environmental control and life support system is among the most maintenance-intensive assemblies ever placed in operation. Its water recovery system, which processes urine and atmospheric humidity condensate into drinking water, contains a distillation assembly with a rotating separator drum, multiple fluid handling valves, downstream filtration stages, and a catalytic reactor that purifies the recovered water by oxidizing organic contaminants. The separator drum has required replacement multiple times. The catalytic reactor requires periodic catalyst bed renewal. Valves throughout the system have failed at various points, requiring crew intervention to maintain water processing while the failed component was isolated and replaced. The entire system has experienced contamination events that forced temporary shutdown and extensive flushing procedures while crew members subsisted on backup water supplies. The oxygen generation system uses electrolysis to split water into breathable oxygen and hydrogen. Its electrolyzer cell stack degrades over time as electrode surfaces oxidize and membrane properties change, reducing efficiency and eventually requiring stack replacement. The hydrogen produced as a byproduct must be managed. The system combines it with carbon dioxide from the cabin atmosphere, using a chemical reactor to produce water and methane, recovering some of the hydrogen's mass as additional drinking water. That reactor has its own maintenance schedule, its own history of valve failures and sensor anomalies, and its own requirements for periodic component replacement. The carbon dioxide removal assembly cycles between two chemical sorbent beds, one actively removing carbon dioxide from cabin air, while the other is being regenerated by heating. The valves that direct airflow between beds have failed repeatedly across the station's operational history, sometimes during periods when the primary carbon dioxide removal system was already operating in a degraded mode, leaving crew members to manage rising carbon dioxide levels through a combination of backup equipment, reduced activity levels, and emergency procedures while replacement components were identified, packaged, and delivered on the next available resupply vehicle. That delivery sometimes took weeks. Across all of these systems and the dozens of others that constitute the station's life support and operational infrastructure, ISS crew members devote between 25 and 40% of their working hours to maintenance and repair under normal conditions. During periods when multiple systems require attention simultaneously, that fraction has climbed above 50%, leaving minimal time for the scientific research that provides the primary justification for the station's existence and annual operating cost. Now carry this maintenance picture to the moon and recognize that every parameter becomes more demanding. Internal systems equivalent to those on the station would need to perform all the same functions, but in an environment where dust infiltrates filtration media faster, where valve seats experience greater abrasive wear from regolith contamination, where polymer components degrade more rapidly under combined radiation and vacuum exposure, and where electronics sustain higher rates of radiation-induced faults. The maintenance demands for identical functions would be higher than on the station, and the lunar base adds an entire category of maintenance that the station does not face at all. Every external system on the surface, solar panels, thermal radiators, communication antennas, rover mechanisms, power distribution cabling, construction equipment, navigation beacons, all of it requires periodic inspection and servicing by crew members conducting extravehicular activities. Each excursion exposes a crew member to radiation, introduces dust into the airlock and ultimately into the habitat, consumes hours of time that cannot simultaneously be spent on internal maintenance, and contributes to the wear accumulation on the spacesuit that must protect the crew member throughout. External maintenance generates internal costs. Internal maintenance competes with external maintenance for the same finite crew hours. The two domains do not add together gracefully. They fight over the same limited resource. The cascade of compounding failures that this creates is not difficult to visualize once you understand the interdependencies. Imagine it concretely. It is the 8th month of continuous occupation. A dust-contaminated valve in the carbon dioxide removal assembly begins sticking intermittently during its cycling sequence. Atmospheric carbon dioxide levels in the habitat show an elevated trend during the overnight monitoring period. The crew traces the anomaly to the valve and determines that replacement is necessary. 2 crew members spend 6 hours partially disassembling the removal system to access and replace the component. During those 6 hours, the backup carbon dioxide scrubbing system operates at reduced capacity. Crew activity levels must be kept low to minimize carbon dioxide production, which means the planned external maintenance excursion to clean accumulating dust from the solar panel array is postponed. The solar panels go uncleaned for an additional 3 days while the primary scrubber is restored to operation. Their output has already been declining from dust accumulation over the preceding weeks. The additional 3 days reduce power generation margin by another increment. The reduced power margin forces the thermal management system to operate closer to its minimum threshold. The following week, a coolant pump in that system shows elevated vibration readings on its diagnostic sensors, suggesting accelerating bearing wear, likely exacerbated by the thermal stress of operating near its minimum flow threshold while the power margin was constrained. The crew must now assess which repair takes priority, knowing that the uncleaned solar panels continue reducing their power budget every day, and that a bearing failure in the coolant pump could cascade into a thermal control system shutdown that would affect every heat-generating system in the habitat. Every decision forecloses another option. Every repair displaces a different task. The crew is perpetually managing the boundary between functional and failed, allocating their finite hours across a list of demands that grows faster than it shrinks. This is not a scenario constructed to illustrate a worst case. It is the predictable trajectory of a complex system operating in an environment that degrades every component continuously. The maintenance backlog does not remain constant. It grows because degradation is continuous and repair capacity is finite. It grows non-linearly because failing systems create additional stress on adjacent systems. And it grows in an environment where falling behind is not merely inefficient but potentially lethal, because there is no fallback when a critical system fails and no replacement parts available faster than the next scheduled resupply. On Earth, if your air conditioning fails during a heat wave, you open a window and call a repair service. If your water filtration system needs maintenance, you buy bottled water for a day. If your power goes out, your house is still structurally sound, still pressurized, still breathable, and help is arriving within hours. On the Moon, every system that fails takes something irreplaceable with it until it is repaired. There are no windows to open. There are no bottles of water waiting in a store. There is no breathable air outside the habitat, and help is a minimum of 3 days away, even in the most optimistic scenario. The maintenance burden is not a problem that gets easier as the base matures. It gets harder. The longer the systems have operated, the closer their components are to the end of their designed service lives. The larger the number of systems that have already been repaired, the more likely that the repairs themselves introduced subtle new failure modes. The more maintenance events the crew has performed, the more worn their tools, the more depleted their spare parts inventory, the more fatigued their capacity for careful, precise, high-stakes technical work under pressure. A permanent base is not a structure that you build and then inhabit while it serves you. It is a machine that you must fight to keep running every day against an environment that is simultaneously working to stop it. And the fight does not get easier with time. It gets harder. Everything described so far, the dust, the thermal cycling, the vacuum, the power arithmetic, the radiation accumulating in human tissue, the bone density silently declining, the maintenance cascade building toward a moment of crisis, all of it exists inside a structure that is connected to the only world capable of resupplying it by a chain 240,000 miles long. That chain is not a highway. It is not a shipping lane with redundant routes and alternative carriers and warehouses positioned at intervals along the way. It is a sequence of precisely executed rocket launches, translunar injection burns, mid-course corrections, orbital insertion maneuvers, and precision landings on terrain that has destroyed multiple robotic vehicles in recent years. Every link in that chain must hold, and statistically, across the operational lifetime of a permanent base, some of them will not. This is the final dimension of the problem, not the environment itself, not the hardware degradation, not the biology. The logistics of keeping people alive on a world that produces nothing a human being needs to survive. Begin with the arithmetic, because the arithmetic is where the difficulty becomes visceral. Launching 1 kilogram of payload to the lunar surface costs, under current commercial pricing structures, somewhere between several $100,000 and over $1 million depending on the launch vehicle, the lander, the orbital trajectory, and the specific delivery location on the surface. These figures will decrease as the commercial launch industry matures and as landing systems become more reusable, but they will not decrease by an order of magnitude within the time frame of the initial base construction and occupation. A modest resupply delivery of a few hundred kilograms of critical consumables and spare parts represents a financial commitment of tens to hundreds of millions of dollars and a logistical operation requiring months of planning, cargo integration, launch preparation, transit, and precision surface delivery. This is not a freight shipment that can be expedited when something urgent is needed. It is a major space mission in its own right. A 4-person crew consumes food at a rate of approximately 1.5 kilograms per person per day on the International Space Station. Applied to a 4-person lunar base crew across a full year, this produces a food requirement of roughly 2,200 kilograms annually, assuming no local food production capability. Water recycling systems on the station recover approximately 90% of available water from urine and atmospheric humidity condensate. The remaining 10% represents irrecoverable loss that must be replaced from delivered supplies. For a 4-person crew over a year, that replacement water amounts to several hundred kilograms. Atmospheric losses from airlock cycling, minor seal leakage, and consumptive processes add further mass that must be replaced unless local oxygen and nitrogen production is fully operational at sufficient scale. Beyond food and water, the consumable components of life support systems represent an enormous and easily underestimated fraction of the supply manifest. Air filtration media must be replaced at regular intervals as dust loading reduces their effectiveness. The chemical sorbent beds in carbon dioxide removal systems have finite absorption capacity and must be renewed. Catalyst cartridges in water purification systems degrade and require replacement. Membrane assemblies in oxygen generation systems lose efficiency over time. Each of these consumable items has a service life measured in weeks or months under normal operating conditions. Under lunar surface conditions where dust infiltration and radiation exposure accelerate degradation, service intervals shorten. The actual consumption rate of these items at a permanently occupied lunar base cannot be reliably predicted from terrestrial or station experience, because those environments do not impose the same combined stresses. It can only be measured by operating the base and observing what actually fails and when. Add to the food, water, and life support consumables the spare parts required to sustain every mechanical system against the accelerated wear the lunar environment imposes. Pump impellers and seal assemblies for fluid handling systems, bearing sets and drive components for rovers and external machinery, electrical connectors, circuit boards, sensor elements, and display screens for electronic systems throughout the habitat. Replacement filter cartridges in sizes and specifications matched to particular systems that cannot be substituted with generic alternatives. Thermal control system components, communications, hardware, medical supplies sufficient to manage the range of injuries and illnesses that can befall a 4-person crew over many months in a demanding physical environment, including surgical consumables, pharmaceuticals with finite shelf lives, diagnostic equipment, and the spare parts for the medical equipment itself. The manifest for a single year of lunar base operations, compiled item by item, runs to thousands of distinct line items, each one representing something the base cannot make locally and cannot function safely without. Each one occupying mass and volume in a cargo manifest where every kilogram costs a substantial fraction of $1 million to deliver. NASA's current plan envisions resupply missions at roughly 6-month intervals using commercial lunar landers. Current generation commercial landers can deliver payload masses ranging from a few hundred kilograms to perhaps a metric ton or more to the lunar surface, depending on the specific vehicle and mission architecture. A base consuming several metric tons of consumables and spare parts per year, while simultaneously receiving new hardware for ongoing construction, requires multiple resupply missions annually. Each mission is an independent operation with its own preparation timeline, its own launch window constraints, and its own probability of failure at some point in the sequence from launch through surface delivery. The probability question is where the arithmetic becomes genuinely alarming. Modern orbital launch vehicles from established providers achieve reliability rates in the range of 95 to 98% for reaching their intended orbit. Lunar landing adds additional risk beyond orbital insertion. The powered descent from lunar orbit to the surface requires an autonomous sequence of engine burns, navigation corrections, hazard detection maneuvers, and final touchdown that cannot be interrupted, replanned in real time by ground controllers, or aborted to a safe alternative outcome once it has begun below a certain altitude. Several commercial lunar landers attempted in the years between 2019 and 2025 failed during descent or shortly after touchdown due to propulsion anomalies, guidance errors, or structural failures at contact. The reliability of commercial lunar landing at the time of this writing remains lower than the reliability of reaching Earth orbit and will improve with experience, but has not yet reached the maturity levels of established orbital launch systems. Consider a conservative overall mission success probability of 95% per resupply attempt, acknowledging that the actual figure may be lower in the early years of base operations and higher as systems mature. If the base requires 4 resupply missions per year to maintain adequate stocks of consumables, spare parts, and new equipment, the probability that all 4 succeed in a given 12-month period is approximately 81%. The probability that the base experiences at least 1 delivery failure in that year is roughly 19%. Over 5 years of continuous operation requiring 4 deliveries per year, the cumulative probability of experiencing at least 1 failed delivery approaches 65%. Over a decade, it approaches near certainty. A resupply failure is therefore not an edge case to be planned against as a remote contingency. It is a statistical near inevitability across the operational lifetime of a permanent base. The question is not whether it will happen but when, what the base will be short of when it does, and how long the crew can sustain operations on their existing inventory before the missing supplies become a survival issue rather than an inconvenience. The answer to that question depends entirely on what the failed mission was carrying. A delivery containing additional scientific instruments or construction components for the next phase of base expansion represents a setback to research and development timelines. A delivery containing replacement life support consumables represents a direct threat to crew survival within a time frame measured by how much inventory was already on hand and how quickly existing stocks are consumed. Inventory management at a permanent lunar base is therefore not an administrative function. It is a survival function. The base must maintain sufficient reserves of every critical consumable to bridge at least 1 delivery failure of the most adverse possible timing, specifically a failure occurring immediately after existing reserves have been drawn down to their minimum operating level in anticipation of an imminent resupply. This buffer requirement significantly increases the total mass that must be delivered and maintained on the surface at all times, adding to the cost of every mission and to the complexity of every logistics plan. Imagine a specific scenario, because the abstract arithmetic becomes fully real only when it is attached to human circumstances. It is the 14th month of continuous occupation. The base is operating near its designed parameters. Systems have accumulated wear consistent with expectations. The crew has managed 2 significant maintenance events in the preceding 3 months, a carbon dioxide removal valve replacement and a partial disassembly of the primary water processing pump to address bearing wear that the vibration monitoring system flagged before it progressed to failure. Both repairs consumed crew time and spare parts from the onboard inventory. The inventory is lower than it was at the start of the rotation, as expected. A resupply mission launched 3 weeks earlier, carrying replacement HEPA filter assemblies for the habitat dust filtration system, a spare pump assembly for the water recovery system to replace the one now showing early bearing degradation again, and several months of food and medical supplies, enters its final descent sequence toward the South Pole landing zone. 30 seconds before touchdown, the primary descent engine throttle valve malfunctions. The vehicle impacts the surface at a velocity that destroys the lander and its entire payload. Mission control confirms total loss within the hour. The next available resupply window, constrained by the alignment of launch vehicle availability, lander readiness, and lunar orbital geometry, is 4 months away at minimum. Emergency acceleration of that timeline is possible in principle, but would require redirecting a lander from another customer's contracted mission or accepting a partially loaded vehicle launched on a compressed preparation schedule, either of which introduces additional risk and cost. The crew now faces 4 months without the filter assemblies and the replacement pump. The existing HEPA filters were already past their nominal service life before the failed delivery was expected to resolve the situation. They remain in service because there is no alternative, operating at reduced filtration efficiency as their media approaches saturation. Dust concentration in the habitat air begins a slow upward trend that the crew can partially offset by reducing the frequency of surface excursions, thereby limiting the dust that enters through the airlock, at the cost of halting external maintenance and construction activities. The crew wears respiratory protection inside the habitat during periods of highest activity, a measure that reduces dust inhalation but adds psychological burden and communication difficulty during work requiring close coordination. The water recovery pump continues degrading without the replacement assembly. The crew reduces water consumption to the minimum consistent with health maintenance, extending the pump's remaining operational life, while accepting that every additional week of operation brings it closer to a failure that could compromise water recycling entirely. If the pump fails before the resupply arrives, the crew must shift to contingency water reserves that were sized to bridge days rather than months. These are survivable adaptations across 4 months. They are not comfortable. They are not what any space agency would deliberately impose on a crew as a planned operational mode. They accept health risks from elevated dust exposure and reduced hydration margins that would be unacceptable under normal conditions. They represent the base operating not at its design point but at its survival threshold, and they leave no additional margin for any further system anomaly during the 4-month interval. If a second system fails during this period requiring spare parts that were on the lost delivery manifest, the crew's options narrow further and the decisions become harder. The 3-day transit time between Earth and the Moon is frequently cited as a fundamental advantage of lunar operations over Mars missions, where transit requires 9 months in each direction. The advantage is real. A crew facing a life-threatening emergency on the Moon is not 9 months from any possibility of help. They are 3 days from a vehicle that could theoretically bring critical supplies, or a rescue crew if such a vehicle happened to be ready for immediate launch when the emergency occurred. In practice, the 3-day advantage is considerably smaller than it appears. An emergency resupply or rescue mission requires a launch vehicle that is fueled, checked out, and ready for launch at the moment the emergency is declared. Launch vehicles in regular operational use are not maintained in a state of continuous launch readiness. Preparing a vehicle for launch takes days to weeks under normal circumstances and cannot be reliably compressed to hours without accepting risk increases that may themselves be unacceptable. A rescue mission to a lunar base in crisis would likely require weeks of preparation even under the most aggressive possible response timeline, during which the crew must manage their situation on existing resources. This means the practical response time to a lunar emergency is not 3 days. It is 3 days plus however long it takes to prepare and launch a response mission. During that entire interval, the crew is on their own, making life-critical decisions with only the expertise present inside the habitat, the information available from onboard sensors and diagnostic systems, and guidance from flight controllers on Earth who are working from the same incomplete information and who cannot physically intervene regardless of how clearly they understand the problem. There is no hospital 3 minutes away. There is no fire department. There is no emergency room where a crew member showing symptoms of acute radiation syndrome, or a developing infection from a wound sustained during an EVA, or a cardiac event that exceeds the base's treatment capability, can receive the care that the situation requires. The medical capability at a permanent lunar base will be substantially more sophisticated than what was available on Apollo, including telemedicine consultation with specialists on Earth, diagnostic imaging, and a range of surgical interventions that trained crew medical officers can perform with remote guidance. But it will not be equivalent to a hospital, and the people receiving care will be the same people responsible for maintaining the systems that are keeping everyone alive. A crew member who is incapacitated by illness or injury does not stop being needed. Their maintenance responsibilities do not redistribute themselves. The other crew members absorb the additional load while simultaneously managing the medical situation and their own physical and psychological stress. A 4-person crew that loses one member to an extended medical event becomes a 3-person crew trying to sustain a base designed around 4-person operational capacity. The maintenance backlog grows faster. The coverage gaps in monitoring and repair expand. The margin between functional and failed narrows. This is the character of the resupply and logistics problem at its deepest level. It is not simply about the cost and difficulty of delivering supplies across 240,000 miles. It is about the complete absence of the informal redundancy that terrestrial civilization provides invisibly in every situation. On Earth, redundancy is everywhere and taken for granted. If one store does not have what you need, another one does. If one repair service cannot come today, another one can. If one hospital is full, an ambulance can take you to the next. If one utility fails, neighbors share. If one road is blocked, there are others. This redundancy is so deeply embedded in the way civilization functions that most people never consciously recognize it. It becomes visible only when it is absent. On the Moon, it is entirely absent. There is one base, there is one crew, there is one supply chain, there is one set of medical equipment. There are no neighbors, there are no alternatives. There are only the systems that were designed and delivered, and the people trained to operate them, facing whatever the environment produces next, with whatever inventory remains on hand, drawing on whatever spare capacity the crew still possesses after everything else the day has demanded. This is the reality that the animations do not show, not because the people making them are dishonest, but because it is genuinely difficult to convey in a visual medium optimized for inspiration. An animation can show a habitat gleaming on a ridgeline bathed in perpetual golden light. It cannot show the 14th month of operations, the worn faces of crew members managing their third concurrent system anomaly, the spreadsheet of remaining inventory being reviewed against the days until the next resupply window, the quiet calculation each person makes about whether the margin is sufficient, and the discipline required to keep working precisely and carefully when the environment and the biology and the logistics are all simultaneously pushing in the wrong direction. That is the moon base that physics and engineering and statistics demand. And the gap between that moon base and the one in the press conference animations is where the real story has always lived. The engineers working on this problem are not naive. They have read every Apollo mission report. They have studied the dust samples. They have modeled the thermal environment at candidate South Pole sites down to individual boulder shadows. They have calculated radiation dose rates using particle transport codes, validated against the Chang 4 measurement. They have mapped the illumination geometry at Shackleton Crater and its neighboring formations with resolution sufficient to identify ridgelines only a few dozen meters wide that receive sunlight for 90% of the lunar year. They understand the problem with a depth and precision that no public summary can fully convey. And they have proposed solutions. Each solution is real. Each addresses a genuine threat with a genuine engineering approach. Each has been tested to some degree in laboratories, in simulation, in low-fidelity analog environments, or in limited demonstration on the lunar surface itself. The question is not whether these solutions exist. The question is what they cost, what they demand, and what they create when you implement all of them simultaneously in the same constrained environment, with the same limited crew and the same fragile supply chain. Because the solutions do not eliminate the burden of living on the moon, they reorganize it. They trade one set of problems for another. And the total weight of all reorganized burdens combined is what determines whether a permanent lunar base is genuinely sustainable or whether it collapses gradually under the accumulated cost of its own countermeasures. Begin with the solution that generates the most optimism in public discussions of lunar exploration. In-situ resource utilization, the extraction and processing of materials found on the moon itself, to reduce dependence on supplies launched from Earth. The concept is straightforward in outline. The permanently shadowed craters near the South Pole contain water ice that orbital instruments have confirmed is present in the upper layers of the regolith. If that ice can be extracted and processed, it transforms the logistics equation in ways that are genuinely significant. Electrolysis of water produces oxygen for breathing and hydrogen for potential use as rocket propellant. A base capable of manufacturing its own water, generating its own oxygen, and eventually producing its own propellant reduces the mass that must be launched from Earth for every subsequent mission. In principle, this is transformative. In practice, every step of the extraction and processing sequence confronts the same environmental hostility that challenges every other surface system, concentrated and intensified because the ice deposits sit in the coldest, darkest locations the South Pole region offers. The permanently shadowed crater floors, where ice accumulates, register temperatures approaching negative 230 degrees Celsius. Equipment sent into these environments must function in conditions that challenge materials at the most fundamental level. Conventional lubricants used in bearings and drive systems solidify. Lithium-based battery cells lose the majority of their usable capacity. Metal components become brittle as their crystalline structures respond to temperatures far below any terrestrial engineering specification. Electronics can fail as thermal contraction stresses solder joints and substrate materials beyond their tolerance. Any machine operating inside a permanently shadowed crater must either carry sufficient heating capability to maintain its critical components above functional temperature thresholds, which requires power that itself must be generated and transmitted into the shadowed environment where solar panels produce nothing, or be designed from the outset with materials and components capable of operating at temperatures that most engineering experience provides no guidance for. The ice itself is not a conveniently accessible frozen reservoir. Orbital remote sensing data from instruments aboard the Lunar Reconnaissance Orbiter and other spacecraft has confirmed the presence of hydroxyl compounds and water ice signatures in the upper regolith of permanently shadowed regions. But orbital instruments cannot determine the concentration, physical form, or distribution of this ice with the resolution needed to assess extractability. The ice may exist as discrete crystalline grains interspersed through regolith at concentrations of a few percent by mass. It may be concentrated in localized pockets where ancient cometry or asteroid impacts deposited material. It may be distributed so sparsely across most of the crater floor that extracting useful quantities requires processing enormous volumes of soil for modest returns. The extraction process most frequently proposed involves heating regolith to liberate water as vapor, then capturing and condensing that vapor for further processing. This requires excavation equipment to gather and transport regolith, heating systems to drive off the water, and collection systems to capture the resulting vapor in an environment where water does not exist as a liquid at any surface temperature. The entire process must operate reliably in vacuum, at extreme cold, using machinery subject to every degradation mechanism the surface imposes, and it must do so at a scale sufficient to produce meaningful quantities of water, potentially hundreds of liters per month for a 4-person crew when drinking, hygiene, oxygen generation, and propellant production are all considered together. No system capable of accomplishing this has been demonstrated on the lunar surface. Small experimental payloads have tested individual components of the concept under simulated conditions and in limited surface demonstrations. The integrated system, operating at operational scale in actual permanently shadowed crater conditions, remains entirely unproven. The engineering is plausible, the operational reality is unknown, and the extraction process imposes its own substantial power demand on a base whose power budget is already fully committed. Heating regolith requires energy. Electrolysis of water requires energy. Compressing, storing, and distributing the resulting gases requires energy. If nuclear power is not yet operational when ice extraction begins, the additional load may exceed what solar generation and stored energy can provide, forcing a choice between ice extraction and other critical functions. The sequencing problem this creates is fundamental. Ice extraction capability requires power infrastructure. Power infrastructure benefits from locally produced propellant that ice extraction enables. Constructing the infrastructure requires resupply missions whose cost ice extraction is intended to reduce. Each capability enables or reduces the cost of the others, but each must be partially in place before the others can reach their design potential. The order in which these capabilities are brought online determines whether the base can achieve genuine resource independence or whether it remains indefinitely more dependent on Earth than the optimistic projections suggest. Regolith shielding is the second major proposed solution, primarily aimed at the radiation problem. The logic is appealing in its simplicity. The lunar surface is covered in regolith. Regolith provides radiation attenuation. You do not need to launch shielding material from Earth. You use what is already there, piling it over and around habitats, until the coverage is sufficient to reduce the radiation dose inside to levels that permit extended human occupation. 80 centimeters of regolith coverage reduces the dose from a worst-case solar particle event to survivable levels and meaningfully attenuates the chronic galactic cosmic ray background. The mass required to achieve this coverage over a habitat module of realistic dimensions runs to dozens of metric tons of material. Moving dozens of metric tons of regolith requires excavation equipment, transport systems, and placement mechanisms capable of performing sustained construction work in vacuum, in thermal extremes, and in the presence of abrasive electrostatically charged dust that infiltrates every mechanical system. This equipment must be launched from Earth, landed without damage on the lunar surface, deployed and commissioned, and then operated reliably for the months of work that regolith emplacement requires before the first crew arrives. Each piece of construction machinery introduces its own maintenance burden. Excavator cutting heads wear as they work against abrasive regolith. Drive systems accumulate dust in bearings and seals. Hydraulic or electromechanical actuator systems experience the same thermal cycling and outgassing problems as every other surface mechanism. The machines require power, which draws from the same constrained budget as every other system, and they require operational oversight, either from Earth, through teleoperation with its inherent communication delay, or from crew members whose time is already fully committed to habitat maintenance and scientific work. An alternative approach to providing structural shielding involves sintering, fusing loose regolith into solid blocks using concentrated solar energy or microwave radiation. Research using lunar simulant materials in laboratory settings has demonstrated that sintered regolith produces blocks with reasonable structural properties and sufficient density to provide meaningful radiation attenuation. The concept has genuine scientific basis, but sintering equipment must itself be designed for the lunar environment, must handle the same abrasive feedstock without clogging or premature wear, and must produce blocks at rates that make covering a full habitat a realistic operational goal rather than a decades-long project. The sintering process also generates fine particulate material during excavation and handling of the feedstock, adding to the background dust loading rather than reducing it. Neither excavation-based regolith emplacement nor sintering eliminates the fundamental construction challenge. Both require equipment investment, sustained power consumption, and operational time measured in months before the shielding benefit is realized. Both generate additional maintenance demands on a crew already managing a comprehensive list of other priorities, and both protect the habitat from radiation while leaving every crew member who ventures outside for an EVA fully exposed to the same environment the shielding is designed to mitigate indoors. Robotics and autonomous systems represent the third major category of proposed solution, and the intuitive logic is compelling. If the lunar surface environment is too hostile for continuous human exposure, use machines for the most dangerous and repetitive tasks. Let robots excavate regolith, clean solar panels, inspect external systems, transport materials, and perform the routine monitoring that currently requires crew members to suit up and exit the habitat. Reserve human capability for the tasks that genuinely require human judgment and dexterity. NASA's phased construction plan explicitly incorporates robotic precursor missions during Phase 1, sending autonomous systems to the South Pole to characterize the environment, test surface operations concepts, and begin delivering and positioning infrastructure before any crew arrives. This is sound engineering practice. It respects the reality that the first human crew should not arrive to an unprepared site and should not be required to perform construction work that machines could have completed in advance. Robots on the Moon face every physical challenge that hardware faces on the lunar surface, absent the biological vulnerabilities but carrying their own specific limitations. They require power. They require communication links to operators, whether those operators are crew members inside the habitat or controllers on Earth. Earth-based teleoperation involves a signal round trip of approximately 2.5 seconds, which is manageable for some tasks and deeply problematic for others. Delicate manipulation, precision placement of components, and rapid response to unexpected terrain features all become significantly more difficult when every command takes 2.5 seconds to arrive and every visual update from the robot takes 2.5 seconds to return. Autonomous operation, where the robot executes tasks based on onboard decision-making without waiting for each command from Earth, requires software capable of handling unpredictable terrain, unexpected equipment states, and novel failure modes without human judgment available in the loop. Current autonomous systems perform impressively in controlled environments with well-characterized operating conditions. Unstructured environments, where the terrain changes unpredictably, where dust accumulation alters the properties of surfaces the robot must traverse or manipulate, where unexpected equipment faults must be diagnosed and worked around without a human technician available to intervene, remain substantially harder. A robot that becomes immobilized by a regolith trap or a dust-jammed drive joint in a location where it cannot be easily reached by crew members may require an EVA to recover, consuming exactly the crew time it was supposed to save. Lunar robots also degrade. Their joints accumulate dust, their bearings wear, their sensors cloud over as optical surfaces acquire dust coatings that reduce sensitivity. Their batteries lose capacity in cold periods. Their electronics sustain radiation-induced faults at rates determined by the same particle environment that affects every other electronic system on the surface. A robot that requires significant crew maintenance attention every few weeks provides substantially less net benefit than initial calculations suggest, because the maintenance time it offloads from one category of crew activity is partially recaptured by the maintenance it demands for itself. The net efficiency gain is positive, but smaller than intuition predicts, and its magnitude depends critically on how reliable the robots actually prove to be under sustained lunar surface conditions. That reliability can only be established by operating them on the Moon for extended periods, which is precisely what Phase 1 missions are designed to accomplish, and which the data does not yet fully answer. Nuclear power, as discussed in the context of the energy problem, is perhaps the most technically credible, long-term solution for the challenge of surviving lunar shadow periods and powering energy-intensive operations like ice extraction. A compact surface fission reactor, providing 10 or more kilowatts of continuous electrical power, would eliminate the fundamental vulnerability created by solar generation's dependence on uninterrupted illumination. NASA and the Department of Energy have been developing toward this capability through the Kilopower program and subsequent efforts, and the engineering basis for a demonstration unit is approaching readiness. But the constraints attached to nuclear power on the Moon are worth examining in detail, because they are often glossed over in the general statement that nuclear power solves the energy problem. The exclusion zone required around a surface reactor, even with regolith shielding, reducing its radius to approximately 90 meters, imposes a geometric constraint on base layout that cascades through every other placement decision. Habitats must be outside the zone. Power cables must traverse it. Work areas between the habitat and the reactor boundary must be accessible for maintenance without exposing crew to elevated dose rates from the reactor itself. On a ridgeline only a few hundred meters wide, 90 meters represents a substantial fraction of the available terrain, and the reactor's placement effectively determines where everything else can go. The reactor requires cooling infrastructure, whose performance must be sustained indefinitely. Radiator panels sized to reject the reactor's waste heat must remain functional across years of dust accumulation, micrometeorite erosion, and thermal cycling. If reactor cooling efficiency falls because radiator surfaces have acquired dust loading that has not been adequately managed, the reactor must reduce output to avoid thermal damage to its own components. Reduced output during a shadow period may not be sufficient to sustain all life support functions simultaneously. The crew must shed load, shutting down non-critical systems to keep essential life support running on reduced power, while also managing whatever caused the cooling degradation in the first place. In its initial deployment, the reactor represents a single point of catastrophic failure for the base's power during shadow periods. Redundancy, the standard engineering response to single-point failure risk, means deploying multiple reactor units, which multiplies the mass that must be launched and landed, multiplies the exclusion zone requirements, and multiplies the maintenance demands on an already strained system. The alternative, accepting single reactor vulnerability and maintaining sufficient battery backup to sustain the crew through a reactor recovery period, reintroduces the battery mass problem that nuclear power was supposed to eliminate, though at a reduced scale. The programmatic path to a nuclear reactor on the lunar surface runs through regulatory approval processes that have no guaranteed timeline. Launching radioactive fission fuel requires compliance with national nuclear regulatory frameworks, international space treaty obligations, and safety analyses demonstrating that a launch failure would not result in dispersal of radioactive material in ways that create public health consequences on Earth. These processes are navigable. They have been navigated for RTG-powered missions many times, but a surface fission reactor is a more complex regulatory challenge than an RTG, and delays in the approval process could push reactor availability past the dates that the base's operational plan requires, forcing an extended period of solar and battery operation that the base's designers knew from the beginning was insufficient for long-term permanent occupation. The phased construction approach itself is a form of solution. By building capability incrementally, validating each system before committing human lives to it, and learning from the actual behavior of hardware on the lunar surface before designing the next generation of equipment, the approach reduces the risk of catastrophic failure from untested assumptions. Phase 1. Robotic missions answer questions that models cannot. Which regolith characteristics at the specific chosen site differ from orbital predictions? How does the thermal environment at ground level compare to what surface temperature mapping from orbit suggested? How quickly does dust accumulate on exposed surfaces under actual South Pole conditions? Where are the unexpected terrain obstacles that landed equipment must navigate? These answers have value that no amount of Earth-based testing or simulation can fully replicate. But phased construction has a vulnerability that is structural rather than technical, and it is the one that has historically proven most difficult to manage. Time. A plan that spans a decade depends on institutional continuity across intervals longer than any single administration's term, longer than most congressional budget cycles, and longer than the typical tenure of the senior program officials who carry the organizational knowledge and political relationships that keep complex programs on track. The history of ambitious space programs is a history of technical ambition meeting political impermanence, and the outcomes are not uniformly encouraging. In 2004, NASA announced the Constellation program, a comprehensive architecture for returning humans to the Moon. The program included new launch vehicles designated Ares 1 and Ares V, a new crew capsule called Orion, and a lunar lander called Altair. Constellation was formally authorized, actively funded, and generating real hardware. Billions of dollars flowed into development contracts. Engine test articles were built and tested. The program had a detailed technical roadmap and bipartisan political support. By 2009, 5 years and approximately $9 billion into the effort, an independent review panel convened to assess the program's status, concluded that Constellation was funded at a level insufficient to achieve its stated goals on any credible timeline without substantial budget increases that showed no signs of materializing. The review was frank about the gap between the program's ambitions and its resources. In 2010, the incoming administration cancelled Constellation entirely. The Ares launch vehicles were terminated. The Altair lander was cancelled. Only the Orion capsule survived, repurposed years later as the crew vehicle for the Artemis program that now carries the moon base aspiration forward. $9 billion. 5 years of active development. Thousands of engineering careers redirected or ended. A lunar return timeline set back by more than a decade. The moon receded from NASA's operational planning horizon, not because the engineering was impossible, but because the political commitment required to sustain a decade-long program through a change of administration proved insufficient. The parallels to the current moon base plan are not comfortable to examine, but they must be examined honestly. A phased construction timeline stretching across 10 or more years, billions of dollars in committed funding whose continuation requires annual congressional reauthorization, commercial partnerships whose financial viability depends on sustained government contracts that may not survive a significant redirection of national priorities. A technical sequence in which each phase depends on the successful completion of the previous one, meaning that a failure or cancellation at any point leaves the subsequent phases without their prerequisite foundation. The moon base announced in March 2026 will extend through at least 2 presidential terms beyond the administration that initiated it. If any administration during that span determines that the program's costs cannot be sustained alongside competing priorities, or that a more visible program such as a direct Mars initiative better serves national interests, or simply that the annual budget request for lunar surface infrastructure is a convenient target for deficit reduction, the base could stall exactly as Constellation did, partially constructed, enormously expensive, and ultimately abandoned with hardware already delivered to the surface, degrading under the same environmental assault this story has described throughout. The International Space Station survived its multi-decade construction timeline, in part because international partnership created accountability structures that made cancellation politically costly for any single nation. Withdrawing from the ISS program would have meant abandoning partners, voiding international agreements, and absorbing the diplomatic consequences of those choices. That accountability kept the program alive through multiple administrations and budget pressures that might otherwise have ended it. The moon base does not yet have an equivalent anchor. International partners are mentioned in NASA's planning documents, and several nations have expressed varying levels of interest in contributing to lunar surface infrastructure. But no binding international commitment, comparable in scope or accountability to the ISS partnership agreements, exists for the moon base as of this writing. The program depends on domestic American political will sustained across an entire decade, and the historical record provides no strong basis for confidence that this will prove reliably durable for programs of this duration and cost. Set aside the political risk for a moment and consider what the engineering solutions cost in aggregate, because this is where the true weight of a permanent lunar base becomes fully visible. The base needs a habitat. The habitat needs radiation shielding, which requires regolith moving equipment, which requires power, which requires either solar panels or a nuclear reactor, which requires a cooling system, which requires radiators, which require dust management, which requires crew time, which requires a healthy crew, which requires adequate food and water, which requires resupply missions, which require launch vehicles, which require funding, which requires political continuity. And each of these requires maintenance, which requires spare parts, which require resupply missions, which requires launch vehicles, which requires funding, which requires political continuity. Every thread leads back through every other thread. The web is not a list of problems to be solved in sequence. It is a simultaneous equation in which every variable affects every other variable, and the only valid solution is one in which all of them are satisfied together, continuously, without interruption, for as long as the base exists. This total system, with all its interdependencies and all its maintenance demands, and all its supply chain vulnerabilities and all its biological constraints and all its political fragility, is what a moon base actually is. Not a building, not a facility, not a destination. A machine with hundreds of interacting subsystems, each degrading at its own rate under the combined assault of dust, thermal cycling, vacuum, and radiation, each depending on the others for the resources it needs to keep functioning, and each generating demands on crew time and supply inventory that compete with the demands every other subsystem is simultaneously making. Keeping this machine running is not a construction achievement. It is not something you accomplish and then move past. It is a permanent operational commitment that continues every day for as long as the base is occupied. The machine does not reach a steady state where it simply runs. It is always deteriorating toward the point where it fails to run. The crew exists, in a fundamental sense, to prevent that deterioration from reaching its natural conclusion. Their entire operational existence on the lunar surface is the effort to keep the machine one step ahead of what the environment is doing to it. The Antarctic Research Station at the South Pole provides the closest terrestrial analog, and examining it reveals both the scale of what permanent habitation in an extreme environment actually requires, and the ways in which the Moon makes every dimension of that requirement more severe. The Amundsen-Scott South Pole Station supports approximately 50 people during the Antarctic summer and a winter-over crew of roughly 40 during the 6 months of continuous polar night. The facility endures temperatures approaching -70 degrees Celsius. Resupply is possible only during the brief austral summer, when aircraft can land on the polar plateau. The station depends entirely on delivered fuel to power its generators. Sustaining this facility is one of the most demanding logistical operations in terrestrial civilization. It requires dedicated supply flights, a specialized workforce of logistics professionals, substantial annual funding, and continuous maintenance attention from personnel who live and work in conditions that represent the harshest, long-duration human environment on this planet. And the South Pole Station sits on a world with breathable air freely available outside its walls. It sits in gravity sufficient to maintain its crew's health without medical countermeasures. It receives no meaningful radiation beyond normal terrestrial background. Its surface material is clean ice that presents no chemical or electrostatic hazard. Emergency evacuation by aircraft is possible during summer months, and even during winter, the option exists as a last resort. The station has called upon it. None of these advantages exist on the Moon. The radiation is worse by 2 orders of magnitude. The vacuum outside the habitat walls is immediately and completely lethal. The surface material actively damages every system it contacts. The gravity is insufficient to maintain crew health, without sustained countermeasures whose effectiveness at this gravitational level has never been clinically demonstrated. Emergency evacuation requires 3 days of spaceflight minimum and cannot be improvised. Resupply cannot be delivered by aircraft on any schedule whatsoever. If sustaining 40 to 50 people at the terrestrial South Pole constitutes one of the most demanding ongoing logistics operations in human civilization, sustaining 4 to 6 people at the lunar South Pole is not merely more difficult by some incremental amount. It is different in kind. The gap between the two is not a gap of scale. It is a gap of category between an extreme environment that is hostile to comfortable human existence and an environment that is actively lethal to human existence through multiple, simultaneous mechanisms that never relent. This is the reality that lives behind the animations. Not because anyone intends to deceive. The engineers know it, the mission planners know it, the astronauts who will eventually live there will know it better than anyone. But the public narrative, the one that drives political support and cultural enthusiasm, and the funding decisions that ultimately determine whether the program continues, tends to compress this reality into words like challenging or ambitious, and then move toward the inspiring vision of what the base will eventually achieve. The vision is real. The science a permanent lunar base could produce is extraordinary. The technologies it would develop for life support, for radiation shielding, for resource extraction, for autonomous construction are directly applicable to the Mars missions that must follow if humanity is serious about becoming a multi-world species. The symbolic meaning of human beings sustaining themselves continuously on another world for the first time in history carries genuine weight that transcends any particular engineering specification. But the meaning does not reduce the difficulty. And understanding the difficulty, precisely and honestly, is the prerequisite for doing the thing with the seriousness it deserves. There is a question that sits beneath everything this story has examined, not whether the engineering is possible, not whether the biology can be managed, not whether the supply chain can be sustained, or the political will can hold across a decade of shifting priorities. Those are all real questions with uncertain answers, and they matter enormously. But beneath all of them is a more fundamental question, one that almost never appears in the press conferences, or the mission planning documents, or the social media coverage of gleaming habitat concepts and confident construction timelines. The question is this: do we understand what we are actually attempting? Not in the technical sense. The engineers understand the technical dimensions with extraordinary precision, not in the financial sense. The program managers understand the cost structures, the budget dependencies, the contract vehicles. The question is whether the public understanding of what a moon base is, what it demands, what it costs in the deepest sense of that word, matches the reality that physics and biology and statistics will impose the moment the first crew settles in, for a stay measured not in days, but in seasons. Because if that understanding is absent, the gap between expectation and reality becomes a political vulnerability. Programs that fail to deliver what the public imagined they were building do not simply disappoint. They collapse. The funding evaporates. The institutional knowledge disperses. The next attempt must begin not from where the previous one ended, but from a position weakened by the memory of a promise that was not kept. Understanding the difficulty is not pessimism. It is the prerequisite for success. Step back from every specific technical challenge this story has examined and look at the pattern they form together, because the pattern is the most important thing. Dust infiltrates every mechanical interface and accumulates in every filtration system and abrades every optical surface and embeds itself in human tissue and requires daily management that consumes crew time that is needed for maintenance, that is needed to keep the systems running that are needed to manage the dust. Thermal cycling fatigues every joint and propagates cracks in every weld and opens microscopic gaps in every seal through which vacuum draws the atmosphere that must be replaced from reserves that must be delivered from Earth on missions, that must succeed despite the statistical near certainty that some of them will not. Radiation accumulates in every cell of every crew member and degrades every polymer seal and damages every solar panel and flips bits in every electronic system and cannot be stopped by any shielding that a practical base can carry, only attenuated to levels that are survivable rather than immediately lethal. Power must never fail because failure ends life support, and life support is what separates the interior of the habitat from the exterior environment that is trying to end the life it supports. Each of these burdens generates demands on resources that the other burdens are simultaneously consuming. Power is needed to manage dust. Dust management crew time competes with maintenance time. Maintenance draws on spare parts inventory. Spare parts inventory depends on resupply. Resupply depends on launch vehicle reliability across years of missions. Launch vehicle reliability across years of missions is less than 100%. The shortfalls accumulate. The margins narrow. The crew works harder to sustain a system that is working harder to fail. This is not a description of a program that is doomed. It is a description of a program that is genuinely, profoundly, categorically difficult in ways that require clear-eyed acknowledgement from everyone who wishes it to succeed. The compounding of these burdens does not plateau. It does not reach a steady state where the base simply runs and the crew simply works. It accelerates, because every system that degrades creates additional stress on adjacent systems, and adjacent systems that are already stressed degrade faster than they would have under nominal conditions, and the combined effect grows non-linearly with time. A base that can sustain itself through its first year faces a harder second year. A base that survives its second year faces a harder third. Not because new problems emerge from nowhere, but because the problems that began on the first day have had more time to compound, more time to interact, more time to consume the margins that were built in, precisely to buffer against them. The margin between functioning and failing does not remain constant, it narrows. And the rate at which it narrows is not the rate you observe in the first months of operation. It is faster. The 12 people who walked on the moon between 1969 and 1972 were among the most extraordinary human beings who have ever lived. They faced risks of a magnitude that most people genuinely cannot process. They sat atop rockets producing millions of pounds of thrust, descended to the surface of another world on engines that had no backup if they failed to ignite, walked across terrain that no human being had ever touched, in suits that were the only barrier between their living bodies and a vacuum that would have ended them in minutes. They did all of this with computing resources less powerful than the device you likely used to find this video. And they left. They left because the missions were designed to be brief, 3 days at most on the surface. Every system they relied on was new, untested in the full complexity of actual operations, degrading from the moment it arrived. The suits were showing measurable wear. The dust had infiltrated everything it could reach. The seals were under stress that would have become critical given more time. Apollo succeeded in part because it was structured to extract its crew before the environment could finish what it had started the moment the lander touched down. A permanent base cannot extract its crew before the environment finishes what it starts. A permanent base is the decision to stay, to remain inside the compounding, to face on day 365 everything that day 1 began and every subsequent day accelerated. The astronauts who will live in that base will not have the psychological anchor of knowing they are leaving within the week. They will have rotation schedules measured in months, in the knowledge that the next crew will face the same compounding they faced, and the crew after that, and the crew after that, for as long as the base exists. This is what living on the moon actually means. Not visiting, not exploring, not conducting a mission with a defined end date and a return vehicle waiting in orbit. Living, accepting the environment as the permanent condition of existence for the duration of the stay. Fighting the dust every day because there is no day on which the dust stops. Managing the power budget through every shadow period because there is no shadow period in which the power can be allowed to fail. Maintaining the seals and the filters and the pumps and the bearings and the electronics because the alternative to maintenance is not inconvenience. It is the end of the air. The true cost of a moon base is not $20 billion. $20 billion is the construction budget for a specific phase of a specific plan across a specific number of years, and it is almost certainly an underestimate of what the actual construction will require. The true cost is everything that comes after construction. The resupply missions, each a major space operation in its own right, required indefinitely, forever, for as long as the base is occupied. The crew rotations, each requiring a launch, a transit, a landing, a handover period, a return launch, a transit, a recovery period, repeated every 6 months, forever. The maintenance infrastructure on Earth, the engineering teams that must be ready at any hour to support anomaly resolution for systems operating 240,000 miles away in an environment that provides no tolerance for delayed responses. The ongoing research and development required to improve every system the base depends on, because the systems as initially designed will not be adequate for indefinite operation, and the improvements must be developed, qualified, and delivered in a continuous pipeline that never empties. The true cost is the permanent institutional commitment, not a program with a defined end state, not a project that concludes when construction is complete. A commitment that continues as long as human beings are present on the lunar surface, which by definition is forever if the base is truly permanent. No mission ends, no phase concludes. The operational obligation simply continues, year after year, requiring funding and attention and expertise and political will in every budget cycle, every administration, every congressional session, for as long as the base exists. This is what distinguishes a moon base from every other space achievement in history. Every previous milestone in human spaceflight had a definable end state: reach orbit, land on the moon, build and occupy the station. Each of these could be planned, executed, and in some sense completed. A permanent moon base has no completion. It has only continuation. The moment you stop continuing, you have not completed the base. You have abandoned it. And everything it cost to build becomes a monument to an obligation that was not sustained. None of this means the attempt should not be made. The science that a permanently occupied lunar base could produce is genuinely extraordinary. Understanding the moon's geological history illuminates the early history of the entire inner solar system, including Earth. The permanently shadowed craters contain a record of ancient cometary and asteroidal material preserved in cold storage for billions of years, a chemical archive of the conditions that prevailed when life was first emerging on Earth. The lunar surface provides a stable platform for astronomical observations of a quality impossible from within Earth's atmosphere. And every technology developed to sustain human life on the moon, every improvement in closed-loop life support, in radiation shielding, in dust-tolerant mechanisms, in autonomous construction, in long-duration human health maintenance, is directly applicable to the missions beyond the moon that must follow if humanity's future is to extend beyond a single world. The moon is the necessary school. The lessons it teaches, paid for in difficulty and expense, and the sustained commitment of people who understand exactly what they are attempting, are the prerequisite for everything that comes after it. Mars is further, colder, more isolated, and in some ways even more hostile. If we cannot learn to sustain permanent human presence on a world 3 days away, the prospect of sustaining it on a world 9 months away becomes something other than a plan. It becomes a wish. But the school only teaches the lessons if the students take it seriously, if the difficulty is acknowledged rather than animated away, if the gap between the press conference and the physics is closed by honest reckoning rather than widened by enthusiastic oversimplification, if the people who must sustain the political will to fund and support a permanent lunar base across a decade of operations understand what they are actually choosing to sustain rather than what the renderings suggested they were building. The moon is 240,000 miles away. On a clear night, you can see it from your backyard, bright enough to cast shadows, close enough to resolve with a modest telescope into individual craters and mountain ranges, and the vast dark plains the ancients called seas. It looks serene, it looks knowable. It looks, after 60 years of spacecraft and cameras and 12 pairs of human footprints, like somewhere we have already been. We have visited. We have not been. Visiting means surviving the environment long enough to leave before it defeats your systems. The Apollo crews were extraordinary, precisely because they managed this, because they operated in an environment that was actively dismantling their equipment from the moment they landed and extracted themselves before the dismantling reached something critical. They brought back samples and photographs and a demonstration of human capability that still resonates more than half a century later. They did not bring back an understanding of what the moon does to things that stay, because nothing designed by human beings has yet stayed long enough to find out. A permanent base would find out, every day, in the condition of its seals and its filters and its bearings and the cells of its crew members' bones, and the efficiency of its solar panels and the inventory numbers on its spare parts manifest. The moon does not reveal itself abstractly. It reveals itself through the specific, concrete, daily experience of living inside a sealed machine that the environment is continuously trying to open. The crew members who will live in that base will understand the moon in a way that no orbital survey, no robotic lander, no brief surface excursion can approximate. They will know the quality of its dust by the way it clogs filters at a specific rate in a specific month of a specific season. They will know the character of its shadow periods by the particular stress those periods place on the power budget of a specific base with a specific configuration of solar panels and a specific nuclear reactor in a specific state of maintenance. They will know the moon the way that people who live in a harsh place always come to know it, not as a subject of study but as the permanent condition of their existence. That knowledge is worth something enormous. It is worth the difficulty. It is worth the cost. It is worth the sustained institutional commitment that no previous space program has been asked to maintain indefinitely, because it is the knowledge that makes everything that comes after it possible. But it must be earned honestly, with clear eyes about what the environment demands, with accurate expectations about what the systems will actually do under sustained assault from dust and thermal cycling and vacuum and radiation, with genuine understanding that the gap between day 1 and day 500 is not a gap across which the base simply coasts on its initial capability. It is a gap that must be actively crossed every day by people who understand what they are fighting and why it is worth fighting. The moon is not waiting to welcome anyone. It is not hostile in the way that implies intention. It simply is what it is, an airless, irradiated, dust-covered world where the temperature swings by hundreds of degrees and nothing was ever alive and nothing was ever soft and nothing was ever forgiving of the slightest mechanical failure or the smallest missed maintenance cycle or the single resupply mission that did not arrive when it was needed. Everything humanity sends there will be tested by that world in ways that nothing has ever been tested before. Every seal, every bearing, every filter, every line of code in every autonomous system, every gram of food in every resupply manifest, every cell in every crew member's body, every political commitment in every budget document. The moon tests everything. And the 12 people who walked on it came back knowing something that the other 8 billion of us do not. They came back knowing that the test is real, that the environment means what it is, that the distance between standing on another world and surviving on another world is measured not in miles but in the daily, unrelenting, unforgiving work of keeping everything functioning against an environment that is content to wait. It waited 4 billion years before we arrived. It will wait as long as it takes to find out whether we are serious enough to stay. A single light burning in a darkness that has known no warmth since before the Earth had oceans. That is what a moon base is. That is what it will be. And whether that light remains burning across years and decades depends not on the animations or the press conferences or the $20 billion or the construction contracts signed on a Thursday in May. It depends on whether we understand, honestly and completely, what keeping it lit will actually cost. The answer, as this story has shown from the beginning, is everything. And it is worth it, but only if we know what we are paying.